The GADT video is out, and we can finally move on to the next part. And the next part is actually using GADTs to implement the machine learning library. We are going to start with this and get back to even. By that I mean there is all kinds of functionality over here, and I want to make all tests work except with the new library. That will be our focus in the main term, and after we get back to even, we'll actually complete the library properly. Recently I've been very busy going to the beach. Some relatives have arrived at our household, and because my doctor told me that I need to do some swimming exercises in order to fix my RSI, I've been going out to the beach, and it's been really exhausting. So I don't have time to do more than maybe 2 hours or 3 hours at most of programming a day. We're going to have to take it slow for the next 10 days or so, but we'll get it done. Oh yeah, from here on out, I don't feel like writing things out in this fucking text box. It's really tedious, and it's easier for me to just speak into the mic. And don't worry, this time, as you can see on this green line, the mic does work. We're going to do the machine learning library properly, and hopefully after we implement the machine learning training, we'll get something good at the end of it. Right now I have a hole in my heart because how shitty the field of machine learning is in this prelude to the singularity. It's all hype, there's very little substance, and big companies are going to lose a lot of money investing in it. But I suppose that's having that happen is good for a change, because usually it's little people who are losing a lot of money on stock market bubbles of various sorts. I don't think, you might argue that the singularity is coming and this isn't a bubble, but I think there is enough time for a break, a crash, and then a proper resurgence. In the meantime, what this will result in is a lot better AI hardware. I personally believe, though, that the current machine learning algorithms and the current machine learning practitioners are about as related to the post-singularity AIs as much as video games are. The video games video games and gamers and graphics cards are what led to this AI hype wave, and I doubt that AI practitioners are feeling a lot of gratitude towards gamers for this happening. It's going to be the same for the current AI practitioners and the actual AI programmers that will come later. What I simply want to do is do the machine learning library properly. I've been pursuing this for like 9 years already, and it's time to do this as it should be. Okay, enough monologuing, let's just start. So what do we do here? I think we won't need these hacky things anymore. We're going to just propagate straight up dimensions. Okay, let me just disable some of this. We don't need this. The weight layers, I guess they could just take straight up dimensions. For now, this is good enough. The input layer, let me think. I guess we'll leave it like this. Oh yeah, and we do need the graph in. Okay, here's what we're going to do. Let's put an existential here. Exists a. Yeah, I just need to think about this a little. Input scalar. I mean, why the hell not? We don't need the model sizes. Later we'll just do a function to maybe redefine the graph using other things, but for now let's just forget it. Input scalar, okay. I guess, yeah, it should exist. Let's copy this. Okay, this for all A. Wait, no, not the graph A, just A. Input scalar rate. Yeah, that's good enough for the inputs. Maybe later we'll actually put keys in the weight layers, but for now, let's just forget it. We had a matrix multiply. Oh, this is fine. Apply. I guess this is fine. Zip. Yeah, zip is perfect. I mean, no, never mind. Yeah, we need to hide the A type variable using an existential. That's fine. Layer state. Yeah, this. Okay, this is perfect. Graph tensor dim A, tensor dim T. Oh yes. Okay, yeah, this is perfect. Layer state. Do we need to pass that thing in here? Yeah, whatever, I guess we do. Graph tensor dim A, tensor dim T. Yeah, perfect. Yeah, this is what we'll go with. Now we can. Now, because we define the graph like this, we can have more than just 3 sizes. I mean, do we want to put in the dim here? Or do we want to just pass in a record of dimensions? That might be better than doing this. Oh, yeah, why not? Let's just do it like this. The actual dimensions are going to be in a hash map anyway. Yeah, and previously we were actually inferring the dimensions of the tensor. Okay, yeah, well... let me just pause a bit so I can think about how I want to do this. But yeah, previously we designed the library, so instead of just a 2-dimensional weight matrix, we were operating on 3-dimensional matrices. This is so we can support ensembles. But right now, yeah, there's no real reason in Okay, in matrix multiplication, to have the tensor be anything other than two-dimensional. I mean, this is intended for two-dimensional matrices, no doubt about that. Okay, the same thing here, and what we'll do, maybe we need to somehow specify the inner dimension of the weight matrix, so it can infer the other dimensions, I think, which are going to be passed into the input matrices, and then it will be applying them. Okay, let me think. How can we infer the outer dimensions of the tensor? I mean, it will just be propagating him through the graph from left to right. So and then it will this weight matrix, if it's three-dimensional, it will be directly applied. Let me think. So this part could be the weight layer, and B, supposedly the B could be an integer or something like that, and wait, A. Yeah, the B could be. This would be the weight layer. B would be something like an input scalar. No, wait. No. B. A would just be the outermost dimension. B would also have the middle dimension, as well as the last one, which is an int. Yeah, I think this could be good. Let's just try going with this. These are just examples from the previous video. We'll remove them. Pointer size, yeah, let's put those in here. Model sizes, model T, graph names, graph concept, graph array. Let's put that in here. Graph offset, model size. Yeah, we don't need the model sizes anymore. Maybe, I mean, this probably won't be the final design, but it's a good first step. We'll bring in the memoirs. We'll just go through all the passes one by one and see what needs changing. The first one is the first thing what we have to do is redesign this whole thing so it fits the new way of doing things. Let's see, unbound variable dim. That's really weird. I mean, where is it going from? Oh yeah, this is just a three-dimensional integer. Okay, graph the top size, model sizes. Yeah, we don't need this anymore. But I think where are we passing in the actual input sizes? That's a bit weird that we don't have that. Oh yeah, here are the dim sizes. What about the input? This is the size block, size mini batch, really? Dim. Oh, I see. Oh, I see. So that's how it works. Yeah, I actually forgot how input sizes worked in the previous library. I guess maybe we could design it to match the old way of doing things. Let me just pause for a bit so I can think about it. Okay. I think that the input node, I mean, not this one, but this one doesn't need an input dimension. We just pass it in through a dictionary. The same goes for this one. Not bad. Not. Yeah, this isn't bad at all. I mean, okay. I mean, we will leave them as input and input scale. I'm just thinking whether we can make a single type for everything. I mean, like, could we do something like this? It's my first time using GADTs, so I'm not sure whether which way would be the best. Back in 2019, I spent some time programming in Clock and Agda and Idris, but I never actually really did a serious project that used GADTs in any of the other functional languages. So who knows? I mean, okay, let's do it like this. I mean, no, let's just do it like this for safety. Now, okay, here we have the model. This is the compiled representation. Yeah, okay, here we have the memoirs. Pass dim. Here are the model sizes. Okay, I guess we're doing that now instead of, instead of what we did to pass the dimensions. So we were passing in the model sizes explicitly. Okay, let's, oops, cache. Okay. Right now I'm thinking whether we should put in compile time references, so we can just set the relevant nodes to a particular dimension. But I will just pass in a record. Let's say record of input dims. This is a very verbose type by my standards. Record of input dimensions. Okay, here we have the, let's name this dims. H-dims. This one is for memorization. I think what we have to do is go to a design that was a lot more similar to what we had previously. Yeah, we did this kind of a hacky thing to get a functionality for ensembles, but we don't need that anymore. Instead, what the hell? Let's just. What we are doing right now simply just it happens when you program. I mean, it doesn't happen to regular programmers, but because regular programmers don't generally decide that their language is missing vital features and then spent like a week or two putting them into the language, but it does happen that you simply designed the library wrong and need to redo it. If the language doesn't have the necessary features, you're pretty much set up for failure. That's the reality. You can kind of muddle through in languages with less power, but you'll fail in the end. The thing about this is, let's think about programming jobs for a bit. Most programming jobs are in dynamically typed languages like JavaScript and Python. So, and they have, let's even include languages like C# and Java into that, because you can use them in a dynamic manner. And most business type kind of tasks don't really require this level of language sophistication. But the ironic reality of programming is that the lower level the task that you are trying to do is, the higher level the language you need to be using is. Instead, you kind of what happens in reality is that it's the opposite. The people that least need very expressive languages are the ones that are using them, and the people that do things like hardware design have absolute trash. So a library like this simply couldn't be designed in anything other than Spiral. You couldn't do this in C++, that's for sure. C++ doesn't even have proper functions. Like, it has closures, but the way the closures in C++ work is very similar to the very old version of Spiral from 2018. They don't have proper types, instead they're just some kind of weird compile time thing. I think Rust does them like that as well. In Spiral, I've very much moved on from that kind of design. So, okay, what was I doing here? Okay, what I have to do is go through the old layers of this file history. Yeah, this is a great feature. Let's see, file history. Layers. Effector graph run. I kind of want to see what was the old version of past themes, because that one had we were passing in a record instead of that what we're passing in now. Region merge, for fuck's sake. Yeah, here we had this get dim thing. Yeah, I just wanted to copy paste that. Whatever, we'll copy paste it and use it as a reference. One of the bugs still in Spiral is that it cannot handle opening something like a previous file from commit. I should really sit down and try to figure out why that is happening. It was just never really important enough for me to bother. Let's see. Alright, I'm in layer GADT. Let me just paste this here. Can I select Spiral? Yeah, but I'm not getting syntax highlighting, unfortunately. Let me just check whether it crashed. No, it didn't. Yeah, we're going to, at some point in the future, have to just simply sit down and make this work. Right now, Spiral projects, the Spiral language server only works on Spiral projects and not when looking through all the files in the commit history and this. So here we have to get dim. This just indexes it from this record of input dims. I didn't want to bother doing this again. Okay, so here we have the dim option dim. Oh yeah, that's for type inference of the weight matrices. Let me think. What do we have to do to make that work in particular? Let me just pause for a bit. I'm back. I've decided what I want to do. We're going to, for both the input layers and the weight layers, we're going to put in the dimensions right inside them. And afterwards, okay, first of all, let me just put in the dimensions and then I'll explain what we'll do. Okay, here we have the key. Let's just have the dim. I mean, this needs to be up here. Okay, this doesn't need a dim. This does, in fact, need it. The reason why we are doing this is to simplify things. Arguably, by having to put in everything directly, all the dimensions, I mean, for the input and the weight layers, things will become a lot less user-friendly. We are losing developer ergonomics by making this decision. In the previous ML library on this graph, we just did we implemented an inference function to infer the actual sizes of the weight and the input layers. I thought about doing the same here, but I realized that because this graph is much more general and powerful, it's actually very difficult to implement inference function in a similar manner. So, but that doesn't matter, because what we're going to do, we're going to implement everything like this, everything that's needed, and afterwards we're going to make a simplified graph just for two-dimensional models. We're going to make something like whatever, union graph to the ensemble. And it's going to be more like this one. So because we'll know what the intended dimensions of the weight layers should be, we'll be able to write an inference function for it. We'll also know ahead of time what the key is for the input and yeah, I mean, we just have the inputs for the. We'll know what all the keys that we need for the various input layers, if there are more than one, which I doubt. You know, it's necessary for us to be able to do more than a single input layer, but it's actually unlikely that we'll have it in a real model. Who knows, maybe somebody will find a use for that. So we're going to do something like have this graph, then we'll compile it to this more general graph. We'll have a graph to the ensemble and make a function to map it to a graph after doing an inference step to put in all the dimensions where they should be. So that's the approach we're going to take. I also had some ideas about, you know, instead of having to use a key here, we could have put in a type, something like dim, not dim, but various dims, and then we'll do something like a function that goes various dims, and then something like that. This would make it a bit more ergonomic, so we don't have to keep indexing into a completely arbitrary type. But that's something that we will do in this particular graph. We don't need to complicate things in this one. We should separate out the functionality from the ergonomics, and then maximize the two separately. So for now we'll just focus on the implementation and not care about propagating the dimensions and everything else. We'll just make sure that the dimensions are in fact there. This is a very good approach. Let me pause for a bit. Let us start. Now let's see, let's go from the top. Okay, at the top we have the weight layer. Now we're going to remove this one. Unlike in the other library, in the previous library, this dimensionality propagation will be unidirectional instead of a bidirectional. Instead of bidirectional, not a bidirectional. It's a unidirectional scheme. Practice my English a little. Now, okay, let's see. Yeah, we're not going to be passing record on input dimensions. Graph the top. Whatever, forget that stupid check. Tensor dim the top. Here graph dims, we don't need this anymore. Wait, graph tensor AB. Dim. We don't need the two different hash sets anymore. Whatever. Okay, and here we have the dim. We're going to be finding out whether this works for real now. Whether GADTs work for real. We've done only very basic tests in the previous videos, and this is a real use case that we're doing right now. Okay, let's go with the input. Where's the input? Exists symbol key, exists symbol key, period dim. Oh yeah. Oh, not bad. In fact, I think we could just group these two clauses. What's the problem? Got C, expected A. Let's think about this for a bit. This C is just a dimension, and this A is also the dimension. And yeah, they could be of different types, so we cannot return them both from the same branch. It makes sense, I think. Does it? Tensor dim T. They should both be dim, I think. Yeah, they're both dim. And okay, this could be considered an error, a language error that we need to fix. Okay, let me pause here so I can think about it. I'm not sure what to think about this just yet. Do we want to even fix this or not? would it be worth the effort to fix it? I need to think about it. Stuff like this in general is why language development can take a while. In a regular language, you learn the rules and you follow them as you program, but over here we are the ones who make the rules. So we have to make sure that we are actually using good rules. That's the point of programming. Okay. This is the most simple example that I can think of where the problem occurs. And these are basically just the identity types. And this is basically the code responsible for it. And the fact of the matter is, I have absolutely zero idea how to fix this kind of issue. Like, is it even possible to somehow adapt the code? The reason why it works for regular unions, which would be something like, let me just do it. No, we'll turn this into a regular union. We just need to get rid of the X's. Yeah, now you can see this works. It works with regular unions because as you can see here, it only requires this particular step. But with GADTs, we have to extract the for rows, then we have to extract the body and the specialized constructor, then we have to unify with the specialized constructor, and that requires a typecase to be filled in. In order to actually somehow, oops, I didn't mean to click on that. I meant, for fuck's sake. Yeah, in order to actually make this example work with GADTs, we'd need to find a way to share the type variables. And you might say, whatever, this is pretty simple to do here. But suppose we had something like if xy suppose we had something like this. Then it would be very hard to unify and share the variables. Yeah, it's basically impossible to do this as far as I'm concerned right now. Maybe in the future I'll think of a way to do it, but I doubt it. Who cares? Let's get back to business. We don't need the ID. And I can't listen to this music while I'm programming, because I need to hear myself speaking. Okay, let's see. What's the map? What's the type of map? DMT, blah blah blah. I guess this should be FA. And let me think. Graph tensor EA. And for all T, tensor dim T. Graph tensor EA. Graph tensor EFE. Okay, I see. E. This is graph tensor E, and I guess, yeah, the problem is, yeah, the dimensions are substituted. Let me think about this. This is the map. Yeah, we're working on a map. Exists A. Graph tensor dim A. So what exactly is the problem here? Let us... A new language feature. This is E. It's instead of the dim, but I guess yeah, suppose we put in a dim, would we get a type error? We wouldn't. Suppose we put in an int. Now we do. So we can be sure this is a dim. We can just let's just imagine that x is a dim. So this is a dim, and we have the f, we have the a, and this a comes from the existential. And why is it... What? Wait, I mean, is it the same dim? We have to be suspicious of the dim as well. For all dim... Okay, let's make it dim top. We have dim t. I guess this could be a language error, but I'm not sure just yet. Let me pause so I can think about it again. I've been doing some testing, and consider this example. If we just assign f to q, it should complain that it's missing some meta variables. Because we are not applying anything to it, it doesn't know how to do the type application to f. That's what this meta variable error is doing. We have the same error here. And in fact, this error is why it's required to use all the for else in the body. Why is it required to use all the for all variables in its body, in its signature? We get the same error here. But when we assign it to Q here, we aren't getting that error. So what's going on is that it's somehow substituting the meta variables with the type variables right here. And then when we try to pass in A, oops, it's saying that it's the wrong type. What? Oh, this kind of makes the error a bit more obvious. It's expecting specific type variables, and it's getting these. You know, let's do a little change before we can fix this, which is not something that I understand how to do right now. Let's change these type variables a little so we can separate them from regular meta variables. This is very annoying right now. Autogen name, autogen for all count. For all in and not just the autogen name. Let's just duplicate it in typecase.
Actually, let's just make it a boolean. Is typecase. Let x equals character. I forget. Let's do in fun. Typecase. Let me just put in a T here and a T here. Now we'll fix the error. I mean the errors. In typecase. In typecase. In typecase. Also, there's also a part here. In fun. In fun. In fun. Let's publish this. I forget this. Wait, we're supposed to run the ML library. Okay, let's see. What's going on? I mean, did not run it, did not compile it. I guess I ran it too early. When I run when the extension is still running, it tends to lock the files, so and as a result, it cannot copy them to the output folder. Methods that are not part of the okay, I mean, we don't need this anymore. What's going on here? TETF. Yeah. Exactly. TETF. TE. Yeah, now we can clearly see that it's substituting these meta variables here with the okay. This is pretty bad, actually. Okay, I understand why this is happening. I just need to figure out how to fix it. That's going to require some thought, so let me pause here. I need to think about it. Let's resume from where we were yesterday. Yesterday I managed to figure out why this error was happening, and now we'll fix it. What we have to do is put this term subst here. We need to duplicate the variables to stop them from being substituted by accident when they are passed into the body of the function. So let's do this. We'll open we'll, factor out typor x-link equals, actually, and this link is a reference and it should be pointing to none. And what we have to do is create a new reference. Typor x ref none. In fact, we can just do typor x. Yeah, perfect. I think this should fix that error that we had. Yeah, besides, I can get rid of this. Yeah, I just wanted to mention that I also did some tiny changes, path and box. I just got rid of the turn subst calls here. And instead, I went into the HO index and HO fun and put this visit t here instead. That should take care of it. No. Let's give it a try. I have this open and I should close it. Oh yeah, perfect. If we uncomment this is a type error. And this thing is still an error, and that's fine. As I mentioned, it would be too difficult to factor out the various cases into one. I guess that's something you simply have to live with GADTs. Yeah, before we actually publish the language, let's just try compiling some stuff in the ML library so I can be sure it still works. Now let's try compiling this. Oh, type error. Oh wait, did I do anything to graph? Graph varies dims. Crap. I didn't mean to break everything. Okay, now we can try compiling this again. Not the learn, but main. Spiral build file. Oh, let's see what's going on. Cannot find the backend. Oh yeah. Okay, I see. In fact, do we even need real course peer? Okay. No, I won't bother going through all of these. Just to remove the type applications. Who cares? Okay. Yeah, what we have to do is change the backend from F# to the CUDA one. Spiral. Then we'll build it again. And let's see. Are there any differences? There aren't. If you look at the terminal, it didn't crash. Okay, I think we're good. Let's just try one. Let's also try Leduc. Yeah, it's the same as before. This is what we'd expect. So nothing shows up in the Git changes section. Okay. This should be FA, I think. Oh yeah, it's a pretty tricky error. Now we just increment, let's see, it's the 10th, and it's version 2, oops. And then, what will we say here? We'll say that we fixed the what? The incorrect recursive function into GADT cases. Oh, perfect. Now what we do? Now, in order to actually publish the extension on the VS Code Marketplace, we have this script that I wrote in PowerShell, and we just PowerShell run. And this will be released on the VS Code Marketplace in a few minutes. Yeah, everything went through here. Now, let's see. I don't feel like waiting until it's released on the VS Code Marketplace, so we'll just work in the extension host. Okay, let's see. Row up, FA, row reduce. Now this one is interesting. If you see how it was done previously, we're just passing in a singleton dimension as the final input of this. I mean, as the last dimension of the operation, or maybe node. I'm not sure how to call it. But right now we have the tensor dim. We have the actual tensor dimensions over here, so we can just trim one of them. Let's see. F. So we could just do first of x, maybe like that, or maybe not. Okay, let me think of it. Here we have the dim. Now instead of a tensor, we are passing in we are outputting a scalar value, and that has the result of just eliminating the innermost dimension. So let's see. Okay, let's do it like this: dim first, dim second. This is dim first, dim second, and it outputs dim first. What is this? Oh. I didn't think about this. Okay, how about this then? this is in an existential. We'll just do dim second. Yeah, this is pretty good. Now we can actually implement the node as it should be implemented. Let's see, what's going on here? Why is it unbound? This is F. What? Got 1, expected 2. Oh yeah, this is dim second. TIE. Yeah, okay, this is pretty nice. Now, first, yeah, this is how you do a row reduce. We have a lot more expressive power now that we have proper GADTs, and the existentials are essential to having the full system working as intended. If we didn't have existentials right now, we have to put it in the output somehow, and that would be a problem. I mean, we have to put this dim second type variable in the output, and that would be difficult. Zip. Okay. Dim. Yes. Oh yeah, we don't have the function here anymore. Let's see, what's the type of zip again? Oh yeah, it doesn't have an existential. Yeah, perfect. Now comes the matrix multiply. And the matrix multiply will be two-dimensional, and yeah, no problem. Maybe. Okay, so this is like MN. Oh, perfect. Now, what are we missing? We have the weight, we have the input. We need input scalar. Oh yeah, we also need the apply. Okay, we have B. So I mean, this trick that we're using here is pretty similar to what we're doing in row reduce, except we are returning the second dimension. Oh yes, that's how apply is supposed to work. Okay, we have the graph tensor AB and we have graph A. Okay. Okay, let's do apply. Apply AB, and what we'll do is let's make it second F A, and I think then that should be fine. There's an existential exists, and A. Yeah, we don't need to go into the B here because there aren't any tensor dimensions in that node. Oh, is this good enough? Okay, let's do something else. Input scalar. And for this, we're just going to error type. Not so. Okay, let's order them a bit better. No, map reduce zip, but well, yes. Great. Oh, this is pretty good. Okay, let's make a commit. Done. What I do? What do I say? Done redesigning pass the new library. Okay, now let's do a search for spiral. Spiral. What's this I574N? I guess maybe somebody did a fork of it and put it on the VS Code marketplace. I mean, let's see, repository. Oh yeah, somebody forked it. This pretty nice. Okay, I guess the language is slowly getting more popular. But you know, I'm not sure whether there's a point in releasing a competing version on the VS Code marketplace. You know, you can talk to me, and if there's something that you need, we can add to the language. Okay, let me think. Yeah, we want to install the latest thing. I mean, sorry about that. I got this was so unexpected that I got distracted. Okay, now I installed the latest version. I mean, just have to exit all the editors and okay, now we are in the version from the VS Code marketplace. So let's focus on the next thing. I'm kind of getting distracted by my own thoughts. I'm thinking about what to do about that version. I mean, it might make things confusing to have two different versions of Spiral on the VS Code marketplace, and who knows. I mean, it's not like it's a popular language by any means, so whatever. I mean, people will see my videos and they'll know what to install. Okay, what do you think? Yeah, this is a pass to calculate the offset. To calculate the parameter offsets. And now, because we're doing everything directly, this will be a lot simpler to deal with. So, okay, let's just copy paste it here and see where that gets us. Yeah, we don't need this dim's body, dim's head. What the hell? Okay, let me pause here so I can think about it. Sorry, I'm a bit scatterbrained right now. When we're doing a time lapse, everything is sped up like 4x, so it kind of just so short periods of where I just think get zoomed past. But now you can see me, standing around and having to decide. Let me just pause for a bit here and then we'll resume. Okay, let's just undo all of this. Going in this direction is completely wrong. Instead, what we'll do is something that's pretty simple. Let's start with this. Get rid of this. Get the dim. And dim, let's make it t, whatever, dim t, and this will be graph tensor dim t. Perfect. Now what we'll do is simply this. Yeah, this was very easy. This is the correct way to do it, and we could, for a node like input scalar which doesn't have a tensor in it, we wouldn't even be able to pass it into the get dim. Otherwise, we get a type error. We can only pass these tensor graph specific nodes. I really love this. Okay, not bad. So what we'll do? Let's what we'll do is move on to the next thing. I mean, there's nothing to do here anyway. Let's just copy paste it. No. Okay, do we need the offset? Yeah, we don't need to pass it forward. Oh yes, it needs to be passed in as an argument. We should also pass in the key. Well, this is... what I'm wondering right now, if we have access to the key right here, this won't be substituted, I think. Yeah, no, yeah, it won't, not yet. Yes, so we'll actually have to pass in the key as well. But the key will be tensor dim t for all dim t, and we'll just put it outside. like here, so the four rows aren't being shadowed by this T here. Now, and we'll just return the dim. Yeah, perfect. And now let's just get the dim's k. Yeah, like this. Okay, in dim equals. And in fact, do we have to return the dim? I think we have to return the offset instead. Yeah, we have to return the size. And I'll just put this here. What we'll do. Okay, here we have the dim, we have the k, tensoring. Now, yeah, we don't need the zipper. F of we don't need the existential. We have G offset, but we also have to pass in the k. And let's see. Let's just copy paste all this. Okay, not bad. Oh yeah, dim first. Now, oh yeah, this needs to be a graph, not a tensor itself. And now, what's the problem here? Oh yeah, we need to pass in the k. K. We need to pass in the k everywhere. Oh, not bad. Okay, now, now what exactly is the problem here? Hashmap get k. Oh yeah, we should be using get the dim, not hashmap get k. Hashmap. Okay, so get dim k. Perfect. Now we have to also take care of the missing cases. Let's see, where's the input scalar? I mean, what do we even do about the input scalar? I guess we'll just return the offset input, and this just returns the offset as it is. Now we also have need the apply node. Do we even have the apply node here? And unfortunately we don't. So and this is one of the issues with not having exhaustiveness checking. We're going to have to do some organization to make sure that everything is ordered properly. Let's see. Yeah, this comes after apply comes after row reuse. Now it's what? Does it have an existential? No, wait, where's the apply? Oh, it comes at the very end, actually, and it has a single existential. And the wait input, apply, input scalar. Okay, so it should come after the wait. Let's do it like that. And it exists A, B, and then what? Then we have to do something about it, and that something is, yeah, which offset A, and F offset offset f offset a. We have to go from right to left, and then f offset b. Yeah, not bad. Are these all of them? Okay, now let's reorganize this one, and this one also needs the apply. Input scalar comes last, and the apply should come here, and these should come at the very end, and the zip should come after rough reduce, I think. Yes. Okay, now we have to exist a b, and then what? Let's see, maybe, okay, f offset a, maybe g, okay, and oops, I meant to put the k outside, and this should be f offset b. Oh yeah, this is good. Offset output. No, we also need the. Yeah, we did put in the apply, no problem. Now there's, I mean, the fact that we don't have the dim in the environment kind of bothers me, but we know for sure that we won't be getting the dim from the hash map in any of the input scalar nodes, because we get a type error in the top-down segment due to calling this. Yeah, this is perfect. I love it. So here we have the param init. Okay, let's also copy this, and we'll see where it gets us. Right now we're just mostly mindlessly translating these cases from the previous library to the new one. And after that is done, and after we've gotten the old tests to run, we're going to see whether what we can do to make the library better. And let's see, we have the assert parameter array, parameter offset. Okay, that's good, that's no problem. Okay, wait and input, and these come at the bottom. Input scalar. Yeah, we can just put that in this one here. And apply has to come after apply. To do. Now we have to go through all these cases. Map. Okay, map. Yeah, no problem. We'll go through all the cases. I just copy all of this. And row reduce exists. Yeah, dim first. And we have the zip. This one doesn't have existentials anymore. It doesn't need them. We have the matrix multiply, and that one is fine. We have. Okay, we're going to make a help function for this. Instead of get dim, we'll get tensor, get tensor, and graph tensor dim t, and it should return then tensor dim t. And for that, let's see, we'll paste this. And hash map get first k, Now we'll get the tensor x, get the tensor x from, okay, this is fine. We have to also apply this. Let's go into fa, fb, and yeah, we need the actual arguments a, b, and exists a. Okay, fine. This is good. Graph a. This is just a typo. Now, yeah, this function is fine. Initializes the parameters of an element on the host. Calculates the output node offsets. Okay, not bad. This one prints all the parameters. We need this one as well. Okay, now we'll copy this. Maybe we can just put it at the top level. Oh no, we don't have the param thing. Whatever, I'm fine with copy pasting this one in particular. Let's see. The weight on the input should come at the bottom. The input scalar should also come at the bottom. Input scalar. Weight, and then what? Then there's apply between them. Then, I mean, these are pretty identical. They're just iterating over everything. So we can put them like this. X get tensor. And then we can just do it all like this. There's no need. Oops. Yeah, not bad. We have the parameter print. Create graph data. Okay. Input extract. Graph offset graph data. Tensor dim input. Oh, where did the dim come from? Oh yeah, the dim here is just a three-dimensional integer. Okay, let me think. Model T-top. Okay. The input. These two come at the bottom. These two are just iterating. I mean, these three. This should be fine. Now we have the zip. Yeah, we need to extract only a single input. Oh, so this is an optional type. Oh yeah, this one doesn't have existentials. I keep forgetting that. Oh, okay. So okay, input access key, symbol key, and I mean, what's the problem? Maybe oh yeah, like that. If the keys are the same, then it gets yeah, then it gets the tensor. It gets some tensor. Okay, let's do this. We'll paste this here, but it needs to be input. It needs to be input and param array, and this needs to be try get. No, it doesn't need to be try get. Sorry about it. And let's see. What should that be? Not param. Oh crap. Here we have the. Yeah, we're using the wrong parameter pretty much everywhere. The wrong array, I mean. Okay, here's the param init. Okay, this is get dim. Sorry, I got distracted for a bit here. I forgot what I was trying to do. Okay, here we have the param offset output, param init. Oh yeah, this is yeah. Here we have the param print. That's fine. Input extract. Oh yeah, that needs to be done from the output. And in pass output we have this h. Yeah, okay, okay, it's fine. We didn't miss as much as I feared. And okay, now what do we do here? We need to get the tensor. We don't need to check whether this is a body node or a head node. Not anymore, because we've cleaned out the library. We redesigned it so that hacky crap doesn't need to be put in here. Okay, let's just get tensor x, and we're getting a type error. Graph tensor dim input is expecting a graph t, and this is graph tensor tmtn. I mean, could it simply be the case that the types are incompatible? Okay, let's okay, roll dim t, and then what's the problem? Yeah, we already have this dim over here in particular. Suppose we do this. Now we have a generic function for getting the tensor from the graph. Tensor dim input. Tensor dim input. Graph tensor tmtn. For fuck's sake. For partition offsets, output array, v. What's this v? I mean, am I doing this right? I'm confused. Fail with Okay, let me pause here so I can think about what's happening here. Oh yeah, what's happening here is that the types aren't matching. Okay, let's do this. Yeah, now the type error goes away. Now let's. I think we'll just copy paste this. Okay. Get tensor x. Okay. So. Why is this an error? I mean, what exactly is it expecting? We have the tensor dim input, and oh, okay, I see. We have to make sure that the types are, matching pretty much everywhere. So, okay, let's make it dim t. Not bad. No, what exactly is the problem? Graph tensor ATB. Oh. Alright, yeah, this needs to be tensor dim input. And what we have to do... Yeah, we know the keys are the same, but we don't have any assurance that this type dim is equal to this type, and that the input type is equal to tn here. So what we have to do is assert that the types are in fact valid. Can we do... Okay, so the tensor... Maybe we could use recreate nominal here. Let's see. Recreate... Or maybe it's a nominal recreate. Yeah, converts a nominal to a different equivalent type. If we have a static array that has a dimension of 2, we can use that to convert it to static array with a type literal of 4. And yeah, it will give us an error if the type is not equivalent. Oh, I really like this. Here's how we're going to... I mean, let's leave it like this, whatever. Yeah, okay, this is not bad. This nominal recreate, we added it during a while back while we were working on type literals in Spiral. And I think I mean, is it even built in? Let's just take a quick look at the core library. Core. Oh yeah, we're looking for the real core. And then what? Nominal recreate. Oh yeah, it just strips a nominal of its wrapper and then recreates it. It's not even a built-in operation. It won't work on union types, but it should work on the tensor itself. If that didn't work, what we'd have to do? I mean, we do something different, and that would be we just assert that the type of x is equal to the type that we need, and then just return it from the real segment. No problem. In fact, this stripping and recreation of the nominals does a bit more than just asserting the types that are equal. It actually evaluates this thing here. I mean, evaluates the real nominal here. So because even though add 2, 2 and 4 are equivalent, they're not equal. And that's an important distinction. But for now it's fine, whatever. We'll get an error if we do something like convert a tensor to a union type, but we won't be doing that as far as I expect. Input extract. Graph tensor extract. Okay, let's see. What's this thing here? Right. I see. Ensemble ID block. Ensemble ID. Oh, okay. This one will require some thought. We don't need to rezip it. We can just zip it normally. Tensor int t. Let me think. This isn't a good type for it anymore. Okay, so what we'll do, okay, let's make this t. Sorry, I had to leave quickly earlier, but today I'm going to take a break from swimming to let my shoulders get some rest, and we have the entire day ahead of us to do programming, so let's do it. I've been reviewing what I was doing yesterday, just so I can remember what I needed to do here, and let's get rid of this. We'll resume what we wanted to do. Okay, this tensor int. Oh yeah, I understand. Okay, let's do dim t tensor dim t. Okay, this is good. Now we don't need to apply these ensemble IDs anymore, because we are not just returning a two-dimensional tensor from the graph. Instead, we are returning the tensor as it is. And instead of, in the actual machine learning model, instead of having the ensemble IDs being applied in their place, we will be using this input scalar node and the apply node. And this will simplify things a lot. Because, right now we no longer have to require that we use ensembles or anything else. If you want to put in convolution neural networks into this at some future point, we can easily do it. Is this good? Yeah, it's good. And we need type checks so we can be sure that it's correct. Output offset, parameter offset. Okay. I mean, just because let me just say, just because it's type checks, it doesn't necessarily mean it's correct, because we're using these compile time hash maps. But regardless of that, I think this is correct. Okay. Let's see. Now we need to go to the next one. This is calculating the dynamic shared memory, and the only node which uses dynamic shared memory is the matrix multiplier. Even though the row reduce and row map should also be using dynamic shared memory, but the shared memory they are using is so low, like 128 bytes at most, that I don't feel like changing it. Okay, this should go at the bottom. Input scalar. Okay, now we have to do this. And I've gotten a good idea. I cannot really listen to music, and it's kind of probably boring for you to just keep watching me when I'm being silent. So let me do one thing. What I've done is turned on desktop audio, and now, oops, I'm supposed to close these tabs, close other tabs. Now let's see. Reverse. this is good. But no, there's one previous pass that doesn't seem right with me, and it's the apply node for it. As you can see, we are always traversing both sides. Here's FA, FB, FA, FB, FB, I mean FA and FB, FA, FB, FA, FB, and over here we're only doing FA. And I wish we were also doing FB. But the problem is that we don't have the dimensions in the second node, so there's nothing really to propagate back. Even so, it might be possible for for the apply node. I mean, no, not the apply node, but it might be possible for us to add nodes which result in the scalar in the future. Maybe, suppose we maybe had a reduced node. Okay, let me just add it to the graph, just for illustration. Reduce, and then for rounding t, okay, let's do this like so, and we don't need the dim here. Yeah, suppose we had something like this, then how exactly would we even take care of it in past dim? Because it has the channel nodes which return scalar, but they don't output a tensor. Okay, let's see. Dim top, T top. Okay, let's try redesigning this. Let's try just doing this, and we'll see where that gets us. Graph T, and it outputs. Oh yeah, this is. Oh, okay. I think I get it. Okay, how about this then? Let's do this like this, and then. Okay, let's make this case tensor. For fuck's sake. Okay, let's do this like so. And suppose we want to take care of a case which doesn't return a dim, then how exactly would that we take? How exactly could we take care of that? I mean, what we're doing here doesn't really have an use case just yet, but I get a feeling that it's important. Okay, let me pause here so I can think about it. No good ideas are coming to mind, which is why we skipped over this last time. I mean, we could always maybe return some dim, or But yeah, the problem isn't the dim. The problem is the lack of dimension. Let me pause here. I had some time to think about what we'll do here. And we're going to have to work, or I mean, think out of the box a little. What's going on here? Okay, let's get rid of this particular case. We don't need it. Maybe I just leave it like this in case I want to add it in the future. Now, here we have the pass dim, and what we're going to do... no, not this. We're not going to have this be a regular pass. Instead, we're going to factor it out. Let's see. I'll just copy this, and then let's name this GADT, and it will have a hash map, and it will return the dim top. Not bad. And now what do we do about this? And pretty much nothing really. Wait, it takes in a record of input dimensions and then ensemble size as the last argument. I mean, okay, this comment is completely stale, and it doesn't return a hash map. Returns the top level takes in yeah, like this. So this is perfect. And now what we'll do is simply replace this with something better, and that something better is this function here. In fact, what we could do, we could even replace this entire thing. F equals dim x okay, now let's see. Here we have the I guess we can just do this like so. Perfect. Now we don't need this anymore. Actually we do, but only for the sake of getDim equals getDim. We'll just partially apply the function by passing in the hash map first. And let's give it an argument, so it generalizes the function. Oh yeah, perfect. getDim. Okay. Not bad. All these two are using getDim, and the others are using getTensor. Since they all need the partition offsets. Not bad. This is, yeah, this is the correct solution. Now we don't have to worry about skipping in the scalar. Instead, it will just dive into the parts of the graph that can be inferred. And we don't have to worry about this being, we don't have to worry about multiple invocations of getDim having polynomial performance, because we are doing memoization. Oh, this is exquisite. Oh yeah, the only problem is that we are no longer making the graph immutable. So what we have to do is maybe set it here. Okay, yeah, what we should do is in fact set it as immutable on both sides here. Now either of these methods will traverse the graph in full, and then after that the graph will be completely in the dictionary, so we can set it as immutable in either of these places. And if we set it to immutable twice, that will just be a no-op. It won't give a compile time error or anything, because we are setting an immutable hash map to being an immutable. Yeah, I think now we have a lot better design. And what we have to do next, oh yeah, so now we're actually running the graph. Oh, that's a big one. Let's see. Graph param output size, we don't have the size anymore, well, T-top. Okay. Layer state. Size ensemble. Oh, I see. Yeah, we have to just instead of iterating over the entire ensemble, we have to pass in an input of inputs for the input scalar node, because that's where it will get the indices from for the ensemble. And we won't be iterating through the entire ensemble anymore. The layer state. I guess the layer state should be input from the outside. Okay, let's do. Okay, ls layer state. It's fine like this, and then indices. Indices. Projective range m blocks in grid block. Do you know that? I mean, I guess we don't. Let's get rid of the loops, and we're going to put the loops somewhere else. This is just to run it for a single iteration, and we have the graph tensor extract. What exactly do we do with this? What are we graph? Graph tensor extract. Tensor AB. Okay, I guess that's good enough. Model M with graph. Okay, I get it. Let's see. Let me just refresh my memory what this does. Yeah, it requires the parameter and the output and returns the tensor. Okay, that's straightforward. Graph T. Wait, input. Okay, let's put these two at the very end. I guess there should be an input scalar. Input scalar. Oh, okay, just a second. Graph tensor extract. Okay, so it will try to get a tensor from here, but if we're going to param offset output, for example, we have the apply node here. What exactly should happen here? Wait, oh yeah, it's getting the dimension from the current node, and we have the get dim, and what's happening in apply? Oh, okay, I see. So it just gets the second part of the dimension. Yeah, that makes sense. Okay, so this makes sense, and let's see. Yeah, we don't need to do anything special. Oh no, yeah, we do. Oh damn it! With zip, we don't create a new tensor for the output, and we shouldn't do that either for the apply. We should just apply the tensor that comes from inside. Okay, let's first implement this. Apply exists. And then, oops, apply loop A with what exactly? We need the inputs. Inputs. real inputs. What exactly? I mean, it should be the input scalar. A graph scalar inputs. Let's make this B. Yeah, but suppose we had something like a reduce here, then could we actually do anything with it? Like, we cannot just extract it, we need to run the graph in order to extract it. And this is, this is kind of a pain in the ass, and this graph tensor extract. So we have the graph run device, and does it necessarily have to, just run the graph? Cannot it also return the tensor, or I mean the graph value, this t-top? If that could be possible, it would be a lot more useful. Okay, let's put this above. Input extract, graph data. Let's put this here. Actually, maybe even a bit further above. Print all the matrix, parameter initialize, pass offset output. Graph tensor extract. Okay. So that's one thing, and it would be very useful if we could combine the functionalities of graph tensor extract and graph run device into a single function. Because that will make it really easy to take care of the scalars. Yeah, I think this is going to be the first serious bit of redesigning. We're going to do what I'm saying here, which is to unify these two functions and merge their functionality into a single one. That will make the library a lot more expressive. If we think about it, this function here is actually what's the core of the library itself. It's where the actual operations are getting executed. So, okay, let's comment this out for the time being. We have the layer state, we have the indices, and that's not bad. Let's see, t-top, model t-top, and we'll okay, let's make this just a simple graph run. Graph run. T-top indices, layer state indices, and we'll return the t-top. fail with to do. And now we can create the necessary hash map as well as the layer state here. I mean, we could also create the hash map in here, whatever. We'll leave the asserts here. Tensor extract graph. We don't have that anymore. And we'll bring this entire thing into here. F something. Hash map create. Memo is H. And this will be from graph T to T. Yeah, perfect. We have the model here. We have the layer state, we have the indices. Okay, so what exactly is the problem? Oh yeah, first we execute that here, but then we do a tensor extract, which no longer exists. So what we have to do is, I think, get the graph directly here. Okay, let's do it like this. Inno A equals FA. What's this G layer state? Let me think. Oh yeah. This we are just partially applying the layer state to G. I remember. So you have the A. We don't need the tensor extract, so we can get the tensor for the current node. That's the only thing we're really missing. It's fine to get the tensor from the bottom level nodes, but we also need some way of creating the tensor for the current node. And for that, suppose we brought this back. Graph tensor extract. Okay, let's do this. Let's just get rid of this. I mean, we don't even need the loop anymore, what the hell. And we don't need the inputs. And what's the X here? I guess the X is the graph. Graph tensor extract, what's the problem? The typecase inputs is unused. Okay. It might be worth it to just fold this entire thing into this one, but I want to leave it outside for now. Now, if you look at the output offsets, offset output, we look at the, let's say, zip. It's not being added to the dictionary because we're not calling G on it. The apply is in fact adding things to the dictionary, and it shouldn't be. it should be much like the zip. Pass through. This is also passed through. The input definitely does need the tensor for its own node. Now, if you ever call graph tensor extract on zip or an apply node, we'll get an error because it won't be in either of the dictionaries, and that's fine. Now let's get out. We have the A, and yeah, this is tensor extract X. Let's just copy the graph. Yeah, the tensor extracting. We'll put it like yeah, this is good. Now, yeah, we actually need to return after this function is being finished calling. We need to return the out. So I guess it might be better to just put it here. Then we call this here. Then we return the out. Okay, let's in that case let's just put it like this. I want to make it a bit more succinct instead of having a ton of crap everywhere. Yeah, perfect. Okay, let's just put this thing in here. No, we don't need that outside, because for the simple reason that I think we use this function in some tests. Otherwise, I definitely just put it right in here. And yeah, and in the tests, we better make sure that we're not calling this on a zip or whatever. We'll give a type error on top level nodes. I mean, not the top level nodes, but on pass through nodes like zip and apply. Yeah, I like this very much. Now we can streamline this whole thing. A equals FA. We also get the out, and we know how to get that. Tensor extract X, and we don't need this join anymore. We can just return the out. And what's the problem here? Tensor TCA. Yeah, this is tensor TCA. The raw map. I mean, it's taking in two-dimensional tensors everywhere. I mean, really? I thought it could take in arbitrary. I mean, it could take tensors of arbitrary dimensions. Let me think. Let me just take a look at the primitives again. Primitives, where are the primitives? There should be in core. No, in TML. And then, if you look at the raw map, Yeah, it's taking a two-dimensional tensor. Then it factorizes it. Okay, let's do this. Let's go up. And you know, we'll make this int. We don't need the dim here. Int. Maybe in the future we'll. In the future, if we need to do a row map, we'll just make something like a flatten first node. So it flattens all the dimensions other than the innermost. For now, let's just do it like this. I mean, this is perfectly fine as far as I'm concerned. Dim first, dim second. Yeah, whatever. We'll get rid of this. And this will just be an integer output. This will be int. And oh yeah, come to think of it, we aren't really checking that the existentials type variable is being used in the body. That might be something we want to do. But never mind that for now. Okay, now we've changed the type of the row map and row reduce. And this will cause a bunch of type errors that will be easily be fixed. Okay, I mean, we've actually fixed everything very easily. We have the row map and the row reduce. Yeah, now we can just do the il a equals also out tensor extract out. I mean, not out, but x. We'll return out here. We don't need those two. Yeah, perfect. Here we have the zip. Now, the zip here is a bit more interesting than last time. Instead of doing the zipping in graph tensor extract, we'll be doing that here. And we don't have that proof function anymore. We can just zip it right here, like this. And okay, inl av equals, and we also need the out tensor extract x, and here's the out. Currently we are hard coding the alpha and the beta here. Maybe we can, add it in the graph directly, but who cares about that for now? It will be very easy to change. Okay, and we just return the out. And here we have the weight. That's just tensor extract x. For the input, that's also just tensor extract x. In fact, we'll probably be able to merge these two. Yeah, we can in fact merge them when they're like this. When we don't, provide explicit arguments. Okay. And for the input scalar, now we have to do for the first time what we've done often in the previous library. And what we've done in the previous library, if you recall, let's see, where is the... Let's go over it. Get dim, cache map, try to get dim scale. I mean, it was something like that. Let me go over all this. Maybe what I'm thinking of was in fact done in the previous version. We had something like a GADT function which was indexing into a record. What the fuck? We'll do it from scratch. Inputs, okay, and k exists. K. And oh yeah, we indices. Okay. Oh, perfect. And I think I'll actually put in a type annotation, and that type annotation should be, yeah, that we are in fact returning a t. A side note: when you do a type annotation in the real segment like this, that type annotation will actually be checked during partial evaluation, but if you do it in the top-down segment like this, they'll be eliminated. Oh, okay, now instead of just calling the f with a unit type, we need to pass in the graph. Oh, now let me think. Yeah, f graph. Perfect. We have the layer state, we have the indices. We aren't looking for anything at all. Sorry, I got distracted. Now, what are we supposed to do? Graph run device. I guess we could just, you know, run the graph and then get rid of it. You know, and then graph run, and then I guess I'll just put in model M. We don't need the layer state here. We do in fact need the indices. Indices. We just return a unit. Yeah, we also need to pass the layer state as a second argument. Okay, let me pause here. I'm very happy with how this actually came out. Runs the graph and returns the result in the top. Is intended used in device. Does not do any checking. Even though maybe it really should be doing some checking. Yeah, let's do that. And not bad. Okay, let me commit here and I'll take a break so I can have breakfast. What do I write here? Redesign. I'll be right back. I'm done with breakfast, and instead of reading those Hacker News comments on AMD's latest acquisition, let's do some programming instead. So we did this. Okay, right now I'm thinking, do I want to return... Should I be returning a value from here, or should I be doing something else? Whatever, we'll leave this as it is. Graph run device, we'll leave this as it is. Graph run host. All of these. Graph run device. It needs the indices. Yeah, what we need to figure out now is what exactly do we want to do with the loop? Previously we were iterating over the ensemble dimensions. Now we have this graph run host. You know what, let's leave this aside. Let's put this in as it is. Map. Tensor dim 10 for all dim. Exists a... okay, I see. I'll copy paste all this. Wait, where are we getting the errors here? Should this be float and the number? Okay. Row of a map. Why do we have an error here? This should be int, I guess. Int. This should be int. Okay, not bad. Okay, let's do, yeah, it should be like this. Then graph tensor int and int. I think this is how it should be. Now comes the discrete sample, and this is calling what? Local discrete sample. Oh yeah, this is row reduce. Tensor. And this is also tensor int. Is it int or something else? I think it should be t. Yeah, I think yeah, it's actually sampling an index, not an element. Here's the matrix multiply. That's perfectly fine. And here's the input. Okay, let's do dim. I think should be graph tensor dim what? Tensor dim what? T. Not bad. Yeah, I think we have everything that we need. This takes care of this takes care of the existing operations. Okay, create the model. Let's see. We no longer have the and what exactly do we have to do here? I'm confused. What exactly is the problem here? Here we have the dims. Oh yeah. Oh yeah. Okay, these dims only needs to be a hash map. Hash map and create. And what? Size. Size is now embedded in the graph itself. I mean, we could pass the sizes in a record and parameterize the graph that way. But never mind that for now. It's more important that we get the library running again. Who cares about everything else? Okay, now we have the test one. Let's start with that. Now let's think what's going on here. Input. I mean, we need to pass the dimension directly. So the input dimension should be what exactly? Blocks per grid, ensemble. Yeah, it's not an ensemble. You know what? Forget about the ensembles. We're going to have to redo this. let's make it 1 4. Text in 4, outputs 4 4 4 4 2. H. This should be tensor int float. Yes. Okay, now we have this like this. No, we just need to pass in the graph. We don't have the sizes anymore. Parameter print model, parameter init model. Oh yeah, no, not bad. We are not running the graph anywhere. Okay, let me pause for a bit here. Let's get this test running, and I think that this should run right away. Let's give it a try. Layers GADT, spiral build file, and don't tell me it crashed. Not this one. Oh, it crashed. The given key was not present in the dictionary, and this is in the pre-pass. Okay, let me think. 999. We're going to have to debug this language error. Remember there being an error on this very line before. 999. Okay. Okay, but now things are going to be more difficult to debug. I will save the commit here. And then, oh, it's in compile pattern. Prepass compile pattern function. Yeah, I think this is probably due to the pattern unboxing in GADTs. Maybe it's not filling in the for alls correctly. Oh wait, actually, no, never mind. Okay, suppose we do it like this. It crashes again. Okay, let me restart it. I want to run it like this one last time. Oh, nice. Okay, I like that this error is here rather than in one of these function calls. It will be easier to debug. Let's try building this. Oh, it crashes. Nice. Okay, so this input here. Input exists key dim. Okay, let's try building it directly. We'll do input, and this will be 1 4. Now suppose we run this, it crashes again, but let's run it from a clean slate just to make sure. Build file. Okay, perfect. This should be easy to deal with. Okay, what we'll do... Okay, let's go into the compilation tests. This is tutorial 1. Let's copy paste this. GADT. Well, let's copy paste the graph. Let's see. Okay, let's go copy this whole thing. We'll put it here, and we'll get rid of all of these except the input. Oh, whatever. Okay, let's do this. Nominal tensor DMT. Whatever. In main. In our main. Okay, now we'll copy this. What did I do? Okay, not bad. Now let's exit all of these so it's not spiral build file. Oh, interesting. If you build this, it actually does work. Okay, what if we... Well, let's put in all of these then. Spiral compilation tests. Nominal layer state, nominal row config. Okay, not bad. Now, suppose we try to compile this. Then it still works. It's not crashing. Wait, if I go into the ML library, I mean, here I have the test one, but we aren't even running the main function. Yeah, usually if you try running it without a main function, you'll get an error. So I'm completely wrong on where the error actually is. I guess we'll just go one by one. We'll comment things out. Graph run device. Oh, so the error is probably here in this getDim function. So, okay, but maybe it's in memorize. Oh, now it cannot find main. Okay, now we have it. Okay, let's just copy this into the other thing. In fact, I mean, okay, let's copy it. Let's just start with that, and we're going to eliminate the we don't need this. Oh no, now graph teams. Let's replace this with match x. Let me just return a function here, whatever function. Oh no, what's the problem? Graph that does not have the map case. What do you mean? Oh wait. So did I forget to save the changelog? It seems like that I did. Looking okay, what I want to do is just have this return unit. Great, now we have this, and what the hell do I do? Let me just run this again. Now suppose we build this, do we get an exception? Cannot find main, in file main, for fuck's sake. First, maybe assert x bool no, never mind this. Let's just get rid of the asserts. Like, who cares? second FA. Oh, whoops. Let's try running this. Yeah, now it's crashing. Excellent. Okay, now the question becomes which variable is it failing to access? Now we can finally put some print statements into the language here. Let's see. Print fn. Oh yeah, so it's happening when it tries accessing a type variable. So, I mean, is it one of these maybe in the existential? Whatever, we'll figure it out. Let's try publishing this. And we'll close this. We'll go into VS Code plugin. We'll comment this out, comment this in. Then once it compiles, we'll run the extension host. We'll close this one, we have this one, and then we'll build the file. Now let's see what it's printing on the top. These are all the type variables that it touches. Oh, so it crashes when it tries accessing the TA variable, and that variable is which one exactly? So it's in this map right here. Okay, that's interesting. The given key was not present in the dictionary. That one should come from the typecase, I think. I mean, it should definitely come from the typecase. Okay, suppose we know that the error is TA, so if suppose TA equals A, then and what we'll do is print out the whole environment in this case. I want to understand what's going on. env and it has a map of terms and types. Okay, so let's also try publishing this. Now if you look at this thing here, we'll build the file and let's check out the output. Okay, here we have the term, the environment. It has A, F, get dim, H, I started to A, dim top, T top. This A is from the existential, dim top, T top, and those are all the type variables that it has in the environment. And it clearly doesn't have TA. So I'm kind of suspicious whether it's okay. Let's do this for the time being, just for a little bit, and we could also just do this. Get dim HA. And we won't actually get an error until we partially compile this. So we can just leave this as a partial function. And okay, what I wanted to do is really check out whether in infer it's filling in the type cases correctly, because the most likely fill type case, there's only one place it should be filling the type case in right now, and that's this one. So we should inspect it. Let x equals print fn oh wait, what? I mean, did I publish it? 153? And yeah, this should be done during parsing, so let me just try it again. I mean, to get this error, we shouldn't even have to run it. Yeah, nothing is happening. So I think it's not filling in the for alls. Now that's interesting. Okay, let me think. Block parsing. No, not here, but yeah, this should be happening during type inference. Let me sit. We have this here, route type case. We have only a single body. Field type cases. Term. I mean, it's only doing that in the clauses and over here. Maybe I'm putting the field type cases in the wrong place. I have no idea. Okay, this is something to think about. Clauses. Okay, we have the match statement. Match row for row fun. Okay, these are just for single statements. The particular match statement that we need is this one here, and it should be going in from the clauses. And okay, let's do that here. What exactly is it doing here? Raw expression. Oh yeah, it's filling in, I think. Yeah, it's filling in the term. But wait, suppose... Oh, crap. Okay, I think I understand what the problem could be. This whole thing, this term, as you can see, it's creating new nodes. But the dictionary that we're accessing to in field type cases needs to work on all nodes. So we are not doing this in the right place. Field type case. Oh yeah, okay. I like this. This could probably be the this most likely the reason why we're getting those weird errors when we try to run the prepass. Okay, not bad. And we no longer need to print out everything. Let's just make it like this. Let's publish it. It's as expected. Writing a real-world program is the best way to find any kind of error. Just by trying to do trivial tests ahead of time wouldn't have done much to ensure the quality of the language. Okay, now let's see. We'll build the file and we'll get a crash, unfortunately. Wait, what the hell? Why is it printing all this shit? These cases should not interfere in fill. It's intended to be called on top level statements only. We're putting a type case in fill. For fuck's sake. Okay, I mean, we should just deal with it properly. Let's see. It has the range, the type expression, and the list of clauses. I mean, we could take care of it here. We could have field type cases call term recursively instead of I mean, this is converting them from a row type, so we only need to call the body. Okay. Okay, we'll do it like this. Let track. And This only needs a recursive term. Okay, whatever. I thought we could also just pass the term as a function into film typecases. But whatever, it doesn't matter. Recturn. This is good. Wait, we also need to term rec term, and this thing. Recturn. Okay, not bad, not bad. Recursive term. I wonder where the actual filling of the 4 rows is happening. Oh, in row recursive block, and maybe it should be happening in null. Oh, it's also happening in row match. It's on the body. Wait. It's. I'm a bit confused. Should I be doing film? Should be filling in the typecases on success, and because what about the body? What about the match body? This is the row 4 on the body, and this is the pattern variable. This body is a conditional of the row of match. Okay, I get it. But then shouldn't I be filling it in the body here as well? Like, suppose we destructure a GADT in only like a single place. Oh wait. Okay, this is the pattern, and this is the success, and this is like the body of the match. Whatever, I won't think about this too deeply. Let's just publish this. I think it should be correct, even though I cannot reason it out right now. I cannot spend the time reasoning about everything. You have to trust your code to an extent, otherwise you'll never get anything done. Okay, did this finish? Okay, it finished publishing. Now let's try running it. Now let's spiral build the file. Can I find main in file main? Excellent. Now let's try running this on the ML library. What will... Okay, let's uncomment everything, memorize, git the team, blah blah blah. Alright, this should also be test 1. I mean, after we run this right now, we should get an error that it cannot find the main. Oh fuck. Default values should have been annotated in fill by pretty best time. Oh damn. Term pattern function. Wait, why is it in pattern function? Okay, never mind this. Let's try. We'll comment all this out. What I'm going to do is try running some of these again. For example, test 3. If I do that, does it crash again? Yep, it does. Okay. So it took a step forward, but then a step back after that. It doesn't seem like it's filling in the default values anymore. Let's see. Fill typecases. Oh, right. Wait, here I have the typecase body, and that's just the X. Okay, that's fine. And we're going over typecase data. Okay, let's do this. Term X. Yeah, that should work. And maybe also make that like. Oh, what's going on? I don't think this kind of parsing error was in the previous version of F#. This probably is something they added in the latest, in the newer versions. Okay, now let's. Yeah, it actually they finished running, and I forgot to remove the print statement. Now, where did I actually put it? Print fn. Print fn. Oh yeah, it's in the prepass. Print fn. Okay, now we'll publish this, and yeah, we need to actually exit this. Okay, now let's let's build this, and we should see nothing. Yeah, and that's perfect. Okay, here we have the layer GADT. Now let's uncomment everything. Now let's try running it. Cannot find the main in file layer GADT. Excellent. In main, let me just raise the table. Now let's try building this. Now what is this error? Cache map has been made read only and cannot be added to. Oh, right, crap. Okay, here's what we're going to do. Actually, I'm jumping to conclusions. I think it's because of this dim here that we're getting this problem, but okay, we shouldn't be too sure. Let's try it out like this. If we build, then what do we get? The inner dimensions of the matrix multiplication node have to be equal. Oh no, what am I doing? Dims. Look, we did it like that before, and right now we are doing a transpose over the inner dimension. So how exactly should this be done? What I want, yeah, okay. Let me pause just a bit. How am I even thinking about this? My god, it's fucking hot in this room. I'm going to get air conditioner this summer. I finally got a job, so I have some money to get that. Usually during summer I'm sweating here like a pig. I could have gone to the beach today, but my shoulder muscles are really in pain. I cannot swim anymore today. So instead of that, I decided to do programming, but you know, for this way, so this will end up being 1 4. Okay, let me think about the matrix multiplication. I mean, we just do a swap here, or do we do the swap in user space? Okay, what I'm going to do is do the swap here, AB. Suppose we have matrix multiplies in the future which allow us to put in a different transpose. Then I don't want to go in here and have to change the dimensions of the weight layer manually. Fuck that. Now let's try compiling this. Let's try running this. Python debugger. Oh nice, it works. Oh, this is just as I remember it. Let's also try compiling no limit hold'em just to see whether it crashes or not. It's not crashing. Fix the... no. Let's publish the new version of the language. PowerShell run. Let's also put in the changelog. Oh, there. 3, and this should be, the date is the 11th. Not bad. We'll do the commit over here. And now we have to wait for the new spiral to get released. I mean, it's this thing again. As far as I'm concerned, they're free to, you know, whoever's working on this, I think I know who that is. He's the guy who sent me an email about Spiral. He did a project in it, and he's pretty much the only person ever to do that. So, and in general, if people want to fork the project and even release it as a plugin, that's fine. But you know, if you do some good work on your own fork, then please consider also making a pull request so we can bring that into the main release. Okay. Yeah. Okay. Whatever. We'll use the version of. We'll use the development version of Spiral for the time being. We'll switch to the you know, the actual version later. For now, it's fine to use the one from the extension host. Let's move on. We have the main pie. We don't need this. Let's go back to the layers. Now comes test 2. We want to get this working. Okay, this is pretty similar to what we had before. Let's get rid of this graph. This is 1, 2. Create a model, input extract, and that should be, yes, the tensor. Input extract model. I mean, oh yeah, now we have to put in the dimension the extracted dimension explicitly. Let's do that. Tensor int. Let's try compiling this as well. Has it crashed? No, it didn't. Great. No, let's do this. Here are the weight matrices. Here's the input answer. Okay, perfect, it works. In the next test, we'll actually run it on the GPU. And we have to figure out. We'll have to do an ensemble model. And we have to do an apply. Okay, let's do it. Let's just copy paste it for now. And maybe we could make the ensemble model a latter test. Looks pretty good. Input 8. Now this should be what? Let's make it 1. This we'll make this. I mean, it has to be 8. It cannot be anything else. Otherwise, we'll get an error. And actually, this needs to be 16. And this also needs to be 16. What exactly? Input. All right. And this reminds me why we even actually redesigned this library, because we wanted to get the input of this matrix multiply and zip it with the... No, we cannot zip it, but we also wanted to output it in parallel with a discrete sample. So we're probably going to have to add a pair node, something like that, into the graph in order to be able to get that. Now let's see. Here's the model. All the sizes are in the graph, so that doesn't matter. Blah blah blah. Yeah, right, we're running it on host. Okay. Me batch and block. And then oh yeah, we wanted to have a bunch of mini batches per block. I mean, and we do need to have at least 16, otherwise we won't be able to even run the example, because the matrix multiplies require have a minimal size. That's how we implemented it. Okay, let's make it a 16. This is like the minimum mini batch. We'll yeah, we won't give it an ensemble. This is good enough for now. We don't need it. We don't need to run it in the model. Let's comment this out. All right. You know, Okay, let me just think about this function for a little bit. Like, okay, just forgetting the graph size from the current model, this is fine. But later, when we get the graph size from something like a pair, what will we do then? Okay, so we'll have to be a bit more fancy. Okay, let's we'll give it the functionality to get stuff from below. Let's do that. Let's do that then. Metric loop. Loop graph. Oh yeah, but unfortunately that means we also need the indices now. If you do this. Oh god, I hate this function. Like I wish we could just do everything in GraphRun. And okay, the GraphRun has the indices. GraphRun device has the indices. Whatever, we'll pass in the indices into this then. What the hell? Indices. Indices. Not bad. Okay, now yeah, we cannot just zip it anymore. I mean, we can. Yeah, it's loop. What the hell are we getting this error? Wait, why are we returning this kind of thing here? Yeah, but then, wait. Now how will we even evaluate input scalar? Okay, this is ridiculous. The only real way to actually get the output is to run this function, and that actually isn't a bad alternative. So suppose we do this. We don't need the indices. We are in fact going to follow this function in graph tensor extract. I mean, it's useless to us now. Then graph tensor extract. Yeah, let's just name it tensor extract. Model with whatever. We only need the graph. let's see. Tensor extract. For a given graph node. Okay, now this is okay, good. Yeah, this also needs the fucking layer state. Oh yeah, it's tough just putting some boolean to extract the graph, but that might not be a good idea either. Wait, input scalar. What about the apply? Do you even... Oh yeah, I actually forgot about the apply case. Okay, I need to pause here and think about this a bit better. It's turning out to be a more complicated issue than I anticipated. I'm not sure what the correct design for this is. I'll be back soon, hopefully. Alright, I think we need to do that. Yeah, so far so good. Now we have to run the graph on the host. Okay, we've taken care of the initial problem. Graph run device, it's fine to leave it like this. Now let's think about the graph run host. We have the t-top. I mean, we'll need the indices. And okay, in this case, instead of indices, maybe we should put in the sizes for the input scalars. And then after we do that, that makes things a bit easy, because we could just do a linear loop or a projective loop. And for the ensemble, how could we take care of the ensemble? Okay, you know, just fuck this. Let's just run it normally. This is just for a test run. We'll pass in an empty record here, because why not? Here we have the run. Now, yeah, we can run test 3 probably. What exactly is the problem here now? Tensor int. Input graph tensor. Oh, okay, I see. And the discrete sample, let's see this thing. It's getting in a t, which is a number. Test 2 is fine, because it's not doing a discrete sample. Okay, whatever. Graph tensor. I mean, it's not. It knows what the dimensions are, and the output is a float. Not bad. Input extract model. Tensor input. Was I doing any extraction? Yeah, I was doing that here. So I'll just use that to replace it. Not bad. Okay, here we have the graph run host model. Yeah, we also want to print out the outputs. And how do we get the tensor output? Well, we use graph tensor extract model. Tensor output. And as for the indices, it should just be an empty record. And yeah, we should actually print it out. And that's about it. Here's the output tensor. Okay, let's give this a try, and then we will do more elaborate tests that have something like a ensemble of weights. What's going on? Cannot apply for all with a term. Wait, the error type only F32 is supported. I mean, what exactly are we passing into the matrix multiply? It's F32. So the error is happening in layer GADT, and get dim. So cannot apply a for all with a term. Why is that happening? Is it on line 67? It's on line 133. Oh yeah, what the hell? Oh, it's in the real segment. We'll just do it like this, but I'm curious which type is it getting. It's typecasing on T, but the T is not. Yeah, it's not an element type. It's a tensor type. Let's see. So what we have to do is tensor. This should be int. And if we really wanted to know what the type was here, we'd have to do a print static, but not the usual print static. We have to use the inbuilt op print and T. Okay. Check the terminal to see which type was being passed in. Oh, not bad. Let's try running this again. And which error are we getting now? Oh, typecase miss. Got. I mean, it's not telling us which typecase did we miss. But okay, it has to be one. Let's see. We have map, reduce, and matmul. Okay, I wish. Okay, how do I put in a bookmark again? I installed some kind of extension for bookmarks in Visual Studio Code, and now to get a bookmark. Yeah, now to toggle it, I need to press Ctrl-Alt-K. Okay, I see. And to jump between them, it's J and L. Okay. Ctrl-Alt-K. And now I'll go to the beginning of the file. Map row, map reduce, matmul, zip weight, input apply, input scalar. Okay, we'll put the bookmark here. Go into next. Zip apply weight input scalar. Zip apply input scalar. Also weight, I think. Yeah, there's also weight. Map row, reduce, matmul. I mean, there should be all of them. Why is it complaining that it missed something? Oh, it's telling me that this is a typecase miss. It's telling me that this is a typecase miss, so... Okay, let me just think about this for a bit. Like, this is a big OR pattern, and I don't think we are addressing that adequately in the type inferencer. Okay, this is another language issue. We could fix it very easily by, you know, just having the tensor extract on the individual pattern cases, but that wouldn't be good. Instead, what we have to do, tf tgth, ti tgth, tk tgth. Oh, why isn't this an error? TFTH, TFTH. I mean, it's the same graph node. Suppose we did something like, you know, this. Yeah, now, of course, so now we get an unification failure. Okay, I'm going to have to pause here to think about this. This isn't a very simple error to fix. I'm not sure how I'll fix it in the end. Maybe we'll make these kinds of cases with GADTs type errors. I'm not sure. And I'm bothered a bit, with this. Here we have TM. Here we have we also have TM, but here we have TK. Here we have TI, and these aren't the same types, I think. Let me pause here. Okay, it was only a few minutes, but I think I already have a good idea of how to fix this. Let's take a look at the path unbox. We covered this code in the review, and as you can see, we are adding the typecase data for GADT typecase. And yeah, that's good, but it would be better if we group the by on this S, like in the OR pattern. Yeah, it should be destructuring some kind of type with a type variable. For all ORs, some specialized constructor. Okay, this is a resizable array. T list and T. Specialized constructor. And this is the body that's going into the pattern. Okay, let's do a search where this is used. It's not used even in very many places. It's basically just in pattern box and here. And now we're doing this fallback where the typecase is one thing, but if that doesn't work, yeah, we're just nesting them in the body, and that's pretty stupid. Instead, we have to, what we need to do is have an else case, something like that. Or group by the clauses. Yeah, what I want to do is, instead of having just a single destructor like here, we should be able to have a list of them. And instead of having this fallback, we should have just a single conditional. And this is this body, but can we really safely group on this? I'm not sure. Can we safely group on this? I think okay, yeah, a single pattern can have multiple GADTs being destructured. So in the light of that, it makes sense why we did it like this. But we should also be grouping on the typecase conditional. Okay, let's comment this out for now. Okay, let's just make it X. Make it like let's make it C, whatever, and then we'll group by on the typecase conditional, and that would be what typecase data, and this is yeah, resizable array. We'll use sequence group by, and the key of that is typecase conditional. There, let's just look at it like this. And then we need the source, and that's just the typecase data. And what we get out, okay, let's do this typecase data. And now it should be a bit more complex. Now instead of just this typecase conditional, we'll replace this with a wildcard. Oh yeah, we'll have the typecase conditional here. We also have the typecase body. But yeah, we instead of typecase data, and this is now a sequence, yes. Typecase 10, and this is just a single conditional. And this then okay, let's do this. This is fun, and we'll do a sequence map and then turn it into a list. This is kind of a pain in the ass. we should just turn the resizable array to a regular array. To array like this, and then we'll be able to use array group by. And why is this causing a trouble? Typecase data. Okay, sequence to array. Sequence to array. Now we'll do an array fallback. This is typecase data, this is just an array. Let's make this cond. And we'll make these clauses. And we'll make this array map. And not just the array map, we need to pass the typecase data. And here we have the cond and array to list clauses. Okay, this is something. And whatever, here we have the for wars and the typecase constructor, we can get rid of that. Typecase cond, typecase data. Yeah, perfect. Yeah, we're doing trimmark X. Oh yeah, this isn't bad at all. This might fix the error, but I'm not completely sure just yet. I mean, it's certainly better than doing what we did before. And yeah, we're doing a fallback. We're grouping on all of these. Yeah, that's perfectly fine. Let's just try publishing this into the, not on the VS Code marketplace, but into the compiler folder. And now we'll try running this. Let's see. Let's try compiling this. Actually, let's first put up the terminal, then we'll run this and it crashes. The given key was not present in the dictionary. It's on line 999. Okay, if we try compiling the previous example, what happens then? It's crashing. It's crashing. Why is this happening? Well, let me just try running it again. We'll even run it on a simplified example. Let's put up the terminal, build file, it crashes. The thing that worked before is crashing now. And the only change that we did is, yeah, it's basically this thing here. We are grouping it. and then we're doing a fold back. And it's not working. Okay, can I think of a reason why this could be happening? For our staircase constructor. No, I cannot think why this is happening. We're going to have to do a step of simplifying the example. We'll have to put in the print statements into the language again. I guess I simply don't understand what's going on at a solution detail. And this is pretty much the pain I have to go through every time I make a new feature. There is no way around it. If I build this, can I find main? God damn it. I mean, let's put it in main, whatever. Get them. Now we have to get that from somewhere. Where the hell? Get. Graph names. Then we have to pass in a graph. Q. Oh, for fuck's sake! I hate this keyboard. I wish that I have this Glove 80 keyboard. It's kind of great, but it also has some issues. One of the issues is that these how do I call them, legs. I mean, the soles of the legs are getting unglued, and another issue is that its software doesn't support the right keys, the right mod keys for these top level ones. So if I type to past while using the thumbs, it kind of messes my flow. I think I should go to their Discord and tell them to update their software. Now what? Here we have the queue. Here we have the queue. We have to get the dim, passing H, passing the graph. Now can we get it to crash if we run this? Fuck it. Yeah, pattern is we have the zip and we're only passing the input. Forget this fucking example. I'm feeling pretty lazy right now. Let's go into the ML library. If I comment this out and I build it, do I get a crash? Yes, I do. Okay, we'll comment things out, much like we did before. We'll just leave the GADT in. And now if I do build file, cannot find main. Okay, fine. If I build this, cannot find main. If I build this, it cannot find main. Now if I build this, oh, it still cannot find the main. If I build this, it cannot find the main. If I build this, it cannot find the main. If I build this, yeah, now it's crashing, I think. So the problem is here. As you can see, yeah, it flickers. And if you do this, it's still crashing. So I can be sure that the problem is here. Let's see, if I do this, it's still crashing. Now let's think about this a little. Yeah, we're inserting the same type, but this one has TATD, this one has TF, and this one is taking TH. Okay, that could be a problem, because you know, in this case it won't even have TH, I think, and these okay, I had good intentions, but that didn't really resolve the issue. Let's also comment all this out. Maybe we can. Never mind. Okay, so we know what the issue is, but is it necessarily the case that it's destructuring them incorrectly, or is the problem something else? Like, could it maybe be unifying? Could maybe GADT unify be doing something wrong? GADT unify GADT. Yeah, we're replacing the stuff inside of here with a specialized constructor. I'm not sure whether doing that with a for all that's already been substituted is a good idea. Oh yeah, we do an initial substitution which substitutes the top level for all with one that's destructured in the GADT. But that just substitutes a for all with a type variable with a type variable. Then in another case it substitutes that with another type variable. Then it substitutes that with another. And you know, by the time it gets to the body, it's only expecting the final case to work. Yeah, that's a bit bad. That's bad. Yeah, this should be a type error. I wasn't really thinking about the OR cases properly. So what I have to do, pause now and think about them more in depth. How will we even fix this kind of error? I'm not sure. We could be stuck on this for a while, for all I know. Let's pause. Okay, I've been thinking about this for like a few minutes. Understand this error a bit better. Here, it unifies the type variable t top with, or maybe just t with this pair, which is expected because it's zipping it. It also introduces a new dim variable. Here, it only introduces a new dim variable, and over here, it also introduces a new dim variable, and this is still a pair. The input also has a dim variable, so a new one gets introduced. And the input scalar doesn't have a for all, so everything stays the same. I mean, the type stays the same. And, you know, I think after thinking this through, we shouldn't have done any changes over here. Even if we don't group them, it's fine if it's not like this, you know. But I think it will have a bunch of nested type cases. It will try to unify, you know, the top level variables with this, then with this, and then with this. And it should go in a chain where new type variables get introduced in the same manner that they were inferred. This is perfectly fine. And well, let me remind myself what happens again if we publish this. No, not DaVinci Resolve. We have to shut this down. If we try building this, then what exactly should happen? I mean, it will... Oh, wait, what? Cannot find main in... Oh, for fuck's sake, this should be fine. And... okay. Yeah, I think the error has to do some... It has to do with something else, not this. Runs the kernel on the device. It cannot find main. Okay, that's fine. And if we try running this, yeah, what's happening? I mean, shouldn't it be crashing or something? Oh, it's not crashing on this test. If we do test 2, if we do test 3, oh, okay, I see. Right. So on this zip thing, it's expecting the type to be F32. That's the essential problem. I mean, no. On the zip node, it's expecting type to be a pair. And all these other types are also expected to be pairs. Let me show you what I mean. No, where is it? Yeah, this is, you can see it's a pair of TGTH. This is also TGTH, 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 TGTH. And it cannot really be anything else. The inference doesn't make, the inference for this doesn't make sense. It's just not general enough. Okay, so we get a typecase miss. I think if we, separated out all these cases, it would go away. But, okay, now I understand what the error is about to begin with. It's because the types being inferred for apply, weight, input, and input scalar are not general enough. But the OR cases should in fact work like that. This should be a pair, and if this is a pair, then this also should be a pair, shouldn't it? Otherwise, how else could this work? Okay, we cannot really undo before we return anything to the body. Right now I'm leaning towards that this isn't a language error. Okay, let me pause again. I want to think about whether there is anything at all I can do about this. Because I don't think the top-down type inference method is broken. And in fact everything is happening as it should, so this is a programmer error on my side. It's simply a problem with me not understanding how the GADT feature should be dealt with. Let me pause for a bit. I come to a decision. This isn't a programming error. We simply come to have to understand that there is a typecase insertion being done to make GADTs work, and that they need to be separated into separate clauses. Now, why is this a problem? Okay, there is tensor extract x, and why is this expecting a tensor? I mean, tensor din t, tensor din... Oh yeah, we don't need this to be a tensor. We could just... not bad. Now, let's see. Yeah, perfect. These need other ways. Typecase. Yeah. Let's factor out this comment on two separate lines. Partial evaluation. Oh yeah, I guess this is fine. But now that I think about it, I think I've been using this kind of pattern in other places, like tensor. Oh, this is actually right, but it would be wrong if we, for example, it would actually be wrong if we did it like this. As you can see now, it's expecting an input scalar where I mean, it's expecting a tensor on the input scalar case, and that shouldn't be happening. Okay, whatever. We got lucky. Oh yeah, but here we have. Yeah, we'll get a pattern miss here. So let's put it at the very start. Whatever. This should be fine now. Graph DK. Perfect. Input scalar, input scalar. And it's by complete accident that I put the input scalar as the first in line. Now if you hover over info scalar, it's just graph to TMTN, TKTL, TITJ, yeah, fine. Okay, let's move on. Let's try building this spiral build file, and let's see what is the error. The type is not supported. Only F32. Oh, that's weird. I mean, didn't we fix that? Oh, there's also this. Wait, oh, this is incalculate dynamic shared memory. Okay, let's see. Let's just copy paste this. In fact, let's copy paste this entire thing. What did it? Okay. This should fix the error. Oh, let's put a print static. Not bad at all. Now let's try building this again. Oh, and it compiled. We have the GADT pi. Now let's try running it. Not bad. Yes, I like this. We're back to even. What did I do? Yeah, I pressed Ctrl E and we're back to even. Okay, that's not bad. Now this should happen long enough for the new spiral to get installed. Yeah, we have the v2.12.3 version, not bad. And I need to close down the manga. And I'm not really listening to this host, original soundtrack, so we don't need it either. We can close this. Now let's just open the ML library directly. What the fuck? Okay, let's close this. Now, if it would only close it, great. Okay, perfect. Oh yeah, this is how we could do a regular deep learning feed-forward model. It would be easy to extend this for recurrent neural networks and convolutional ones, but what we do want is an ensemble model. So that's what we should focus on next. And the thing is, now the matrix multiply is expecting a 2D input everywhere. I think, yeah, we literally set it like that in the graph itself. Yeah, here we have the tensor int as the input, tensor int as the second input, and tensor int as the output. That's perfect. The problem is how exactly will we get an ensemble? And we have to combine the matrix multiply nodes. Okay, let's do a matmult ensemble. This will be... And you know, it's always a bad idea to do AB as a dimension. It's better to do something like BA, and then this could be AB, and this could be CAB, CBA, and this will be like CAB. And unfortunately, as you can see, we're getting a type error. It's expecting a pair, and we're giving it an int. So what we're going to do is finally use the apply node. And the first input is this weight node. The second input is input scalar. And what exactly? Yeah, we need to pass in the key. Okay, I will pass in the key exists. And ensemble. Exists ensemble. And this should return let's see, graph int, I think. And this will be why the hell is it acting like this? And oh, I see. This needs an existential exists. Do we need the type annotation here? I don't think we do, but okay, maybe we do. But we can probably work around that. Let's just put an annotation for this. And this should probably be yeah, I mean, it doesn't make sense to use anything but float 32 right now. But we'll leave it like this. Maybe we'll add other data types in the future, so there's no point in being overly restrictive here. So yeah, now we have the matmul ensemble. Oh, now let's do an example that computes over the entire ensemble. And test whether it's running an ensemble model. Test running okay, this is example 4. This is matmount ensemble. Of course, all the inputs here have to be of the same size. Okay, ensemble equals, let's make it like 16. And this is an int. So it doesn't really matter. Like, we have matmount ensemble, and we know that it's taking an int as the first input, so it will unify with it and tell us that we have an int here. Okay, matmount ensemble. Not bad. Now it will create the model, it will extract the input. Oh yeah, the same input is getting passed through every node in the ensemble. Copy to, graph run. It runs the graph on the host. Okay, let's take just a look briefly at the previous. Yeah, loop linear size ensemble. All of that will go into loop linear. Okay, if I could only stop hitting the wrong key. Now we'll be passing in the ensemble as a part of the input. And if we try running this now without the wait, why is this happening? Oh yeah, I don't know how to use my own keyboard. Oh yeah, we also need to modify this. We just pass in an empty array. Okay, where is the graph run host? Sizes. And what we'll do is do a loop linear over all the ensemble dimensions. Sizes. How did that go again? Okay, so full sizes. Actually, this should be indices. And we'll pass that in here. Okay, no. Okay, I mean, this is perfectly fine. I like this solution. The only problem we'll have later is dealing with the block sizes. Maybe. Maybe for the block we could. Maybe we could introduce a special block node in the graph itself. Just something like apply block, and that would deal with the problem of applying the correct mini batch. Because the previous example did have like 3 dimensions for the inputs, and that's 1 dimension for each block. I mean 1 input for each block. We'll probably go with that solution because otherwise it's actually it's not really a problem to pass the block size in here. We could do. Okay, let me just think about it for a bit. Here we have the block. This is the mini batch. Are we doing anything with the mini batch anywhere? What about the block? Okay, let's just put in a block. It's perfectly fine to do this. I mean, to do this here. Indices with block equals thread index and expect a record God sizes. I'm gonna just do this in the real segment. Yeah, the real problem is actually extending this in the top-down segment. It's kind of tricky. But yeah, okay, I understand what we'll do. We'll just pass things like this, and then later we'll add a apply block node to the graph. And in that apply block node, we'll check that the outermost dimension has the correct block size. That will take care of everything. We don't even have to care about that here. The current block we can just get as thread index. I think if you look at Corcuda base, let's see, where is the thread index? Or maybe, yeah, we can just use block index. Bam. Block index. Apply block index, yeah, we'll just do it like that. And now we have test 4, and this one tests the ensemble. We'll also add a mini batch of block inputs, something like that. Okay, let's just run this for now. Build file. We get an error, of course. And what is that error? Typecase miss graph I32. And yeah, of course, and the input is expecting some kind of a tensor. Oh yeah, I really walked into this one. Okay, this is a good lesson for me. Let's not mix. Let's not use OR patterns in GADTs ever again. Amateur mistake of a beginner who doesn't even know how to use GADTs. I keep doing this everywhere as if they were regular union cases. Now we're getting an error again. What's the error? Wait, what? I mean, didn't I get rid of all of these cases? I mean, probably not. I missed this one. Okay, which one was there again? Cannot find the offset in the dictionaries. The offset for what exactly? Oh, wait. If did I actually put in the... Oh yeah, we have the input tensor extract here. Oh yeah, so it shouldn't be triggering in that case. Whatever. We'll do a print static. And actually, we'll do a regular one. Print static x. Check the now let's see, what will we get in the terminal? Wait. It cannot find the offset for the weight layer. Okay, well, how is that possible? Parameter offset, and wait, which weight was it? I think this is the last one, maybe. 1616. Oh yeah, it's this one. Ensemble. This is actually very weird. Like. Let me think. If we build this, we don't get the error. If we do... Wait, could the problem be that it's not going into apply? Oh yeah, let's check the pass. Here you had the pass offset parameter, and what's happening in the apply? I mean, it is going in the apply. Oh yeah, but we aren't using no, we don't need to add it explicitly. We only need to add it in K. What's going on? Okay, let's do a print static K. We'll bring up the terminal. And yeah, it definitely should be putting them in the offsets, the partition offsets dictionary. Why is that not happening here? I need to sit down. subset output. Configuration memory, extract tensor, graph tensor extract. Oh, god damn it. Okay, that's one issue resolved. Let's try building it again. Oh, it has a type error in the path somewhere. Unbound variable x. Check the output in the terminal. And now we build it, and it builds. Now we run it, and it runs, and we'll see what gets outputted. There should be several outputs, and not just a single one. Yes, yes, yes. Wait, 3, 4, 5, 4, 5, 8, 1, 5. Okay, this is weird. I mean, why is it outputting the same array over and over? Oh yeah, it's extracting the graph. Oh, I see, but we don't have the multiple outputs anymore. I forgot about that. Oh. Oh yeah, that's one change from the previous example. We might want it to keep track of the multiple outputs. How could we do that? Well, the first issue is that this discrete sample doesn't even take in an output. All the nodes have their own outputs. Okay, here is I mean, we could go into the map row reduce and row map nodes and add an optional output node. That's what I'm thinking of doing right now. And then if you had the optional output node, like an optional graph node for the output, we could do an apply with an input scalar, and that would work perfectly. And we should do that. We should definitely do that. And I need to overcome my laziness and actually do it. Let's do it. It's like, you cannot see the time in the bottom right corner, but it says 4:22. We could do this for a while longer. I think, okay, I'll put the math model node here. I guess this one could also use an output node. Do we want to keep all these output nodes? Craft tensor dim A. Okay, let me pause it just for a bit. Okay, let's get started on this. We'll put in. Okay, I mean that's one thing, but how do we even create a regular node? Because those nodes aren't the input nodes, they aren't the weight nodes. So should we just add the output node? Okay, let's first add the output node. Well, does it need a key? I mean, why not? Let's have it hold a key. I mean, in that case, there's no real difference between it and an input node, so whatever, we don't need the output node. And we can then just apply it. Output apply. And now, okay, let's put in an output node. Option. This is the optional output node. And I need to lighten up this a little bit because there are too many nodes everywhere. And the input is an int, the output should be an int. And this should be option. No problem. And this should be an int. As for the matrix multiply, you know, whatever. Let's just work on these three for now. And now we need, you know, like special behavior for checking the output node. Okay, check out. Okay, let's make this like x, whatever. Then match out it some x, and then we have to assert x equals x, the dimensions of coming from the input and have to match. And if they do, I mean, whatever. If there are none, then we don't need to do any type checking, and we'll just return the out. Okay, so we can just make this something like option m iter fun x, and everything's like here. Option m iter Then we'll just do a check out. Why is it causing trouble? Oh yeah, because this is an option graph and not an... Okay, So... we have to do maybe this f of x. We have to do a recursive call. Check. Check. And we have to do a bunch of work in the other pass offset parameter. Okay, now but I think I mean whatever. Let's just do this thing. I mean, we don't need to add this same kind of check, but we do need if this is like sum, then we do need to do something like okay, g x out equals then what? If match out with then if it's sum, then we need to call f let's make this offset x why is it bitching at me? Recursive functions with for alls must be fully annotated. Okay, for all graph t, for all t, and this should be graph t, and it should return size, and this should be, and the offset should be size. Some. Oh yeah, this should be option t. Option graph t, I mean. And if it's none, then return the offset. And yeah, we need to put in the g here. G out. Out, and this needs an out. This needs an out. Okay, now we also need to do something about this. Okay, here we have and all these have out, but one doesn't. Where is it getting the offset? Yeah, here it's getting the offset directly. Okay, let me pause here so I can think about this case. We need to somehow get the offsets from the output node instead of just calculating them right then and there. I have thought about it. Here's how we're going to do this. Let's make this out, and this will be option. And now we'll just pass the out into G here. Out. And this will get none, this will get none. And now, if there is an output node, match out with... Okay, let's make this the none case. Oh, this is perfect as the none case. And now, if it's sum, then we have to do what exactly? I meant to put in sum, not sun. Now we need to get the offsets from this somehow, and this is this is getting the dimension of the k. Then it needs to get the dimension, offset equals. Okay, this needs to be recursive, and this needs to be end, and I guess he's complaining that this needs to be fully annotated, or maybe not. The first statement of a recursive block needs to be marked as recursive, but I thought I did that because this is rec. There's a parsing error here. Okay, no problem. And then we just need to count the f with the current offset. Yeah, I think, with the current offset. And X as a key. Okay, that will give us a new offset, but is this... why is it calculating the offsets here? No wait, this needs to be the new offset. Okay, I understand. Offset new assert offset the A new output offset has to equal the one in the output node. And then we can just return offset new. Yes, like this. Oh yes, this is interesting. There's no real need to compare dimensions. We can just compare the offsets. But I think we're also comparing the dimensions. Let's see. Yeah, we are. There is plenty of safety checking being done. Not bad. And now, if you look at this, we can notice that there's a lot of duplication going on. And so, what exactly should we do here? We should factor this out. Okay, let's factor this out. I think we can just move it to the beginning like this, and yeah, we can just return the offset new in the none case. And over here, yeah, we have to do a bunch of things. We can even just factor this out and then do the option M iter, and this will be out, and this will be fun x equals f offset x. We can just return the offset new as it is here. Yeah, this is how you factor things out. You can you can duplicate things, and then it will make it easier to see where the actual duplication is going on after you modified the section. It's easier to do that than try to factor things out ahead of time. It's one technique that experienced programmers use. Now, okay. We have the output offsets now. Then we need the dynamic shared memory. Okay, no problem. Rec G T. Okay. X option graph T. And then we get back the size, and this will be and then we match on x, match x with. If it's none, then we just return 0. If it's some, we just return what? What do we return? We return f of x. I mean f of x. And now we have to figure out how to actually use that here. Do you want to do the max manually? I don't feel like it. Okay, let's do size, max size and then we do g f of day and out yeah, and there is the parameter initialize. Oh my god, there's so many of these. I'm dying here. But we'll get through this. Invalid g option function none sum x f of x and inal out g out we have to print the parameters as well. Yes, that's more of the same. Let's just do this. We have to extract the input. Okay. Yeah, the input could also be in the output node. Let me think. Oh yeah, they definitely shouldn't have the same ensemble key. Okay, let me sit down for a bit. Okay, let's copy paste. Oops. For fuck's sake. And this will take in the output. We need all of these. Out. X. T, option T input. Input and match x with sum x. We can just return the x or maybe sum x. What's the problem with this? Oh yeah. It should return the tensor dim input. Tensor dim. If it's none, then if it is none, then we need to evaluate the output. We need to match whether it has the output. Match out with let's say sum x f of x none. The none case. The none case would do what? The none case. Yeah, we just return the original, I think. whatever. I mean, the run case is just none. And then... and... okay, G... G, and over here comes the out. Out. Let's just copy paste this. What the hell do you do? Oh, not bad. That should take care of that. Extract the tensor, top level node. Wait, what do I think about this? Well, they should have the same offset. They should have the same offset. So... oh yeah, but the reason why we need to go over this, because the input layer could be in the output node. But over here we don't need to care about that. We just need to extract the offset from the current node, and those should already be in the dictionary, as they are. Okay, let me just do some checking. Pass offset output. Yeah, it calculates the partition offsets from the current offset, and then it outputs a new one. And we are just requiring that the output of the offset of the output node matches this one. That's okay. Wait. Will that actually, that won't be the case at all. Like, and the output of a map node could be like 2D, and it only needs a subset. But the output could be 3D and could be much bigger than the actual, expected output from a map node. Oh, so this isn't correct. What the hell? What are we doing here? Okay, this is bad. I'm going to have to pause to think about it, because this isn't the way I intended it. Like, definitely not. I messed up the design. Let me pause. Okay, we got this wrong. What we'll do... let's see, match what exactly? Out with the non-offset new. And if it's sum, then we have to do an assert. But it's not going to be the same assert as before, but instead in offset new like this, and it's less than a recall. Offset new, and This is how it's going to work. Now the output offset can be a lot bigger than expected. Now that I have this, we can contract the ensemble dimensions in the output. Now, okay, so that's one thing. The pass to calculate dynamic shared memory, that's fine. Yada. Writer init. Yeah, everything is nice and recursive. Input extract, graph tensor extract. Now this is no longer as straightforward as one could expect. We cannot extract the output just from the current node. It has to map row reduce. Yeah, we need these two. Okay, let's do it like this. This is the actual execution. Apply zip. And we'll do this is But now I actually need these two functions to call each other recursively, and that means this one needs to be passed a hash map. So okay, maybe maybe tensor extract. No, I cannot accept this design anymore. I really want this function to, if a node has an output, then it should get the tensor from that in particular and nowhere else. So, but how do we make it recursive without, you know, having to pass in a hash map and all this crap and layer state? I mean, one answer is to just fold this in, and but you know, if we weren't using this anywhere, that would be the solution. But I think we are. Well, let me. Yeah, we are using this in two places, and this function is clearly useful. So we should be able to call it in a naked fashion. Oh, hash map mcreate. I mean, is it a problem if we pass it a hash map? It will probably be a problem if we pass it on the layer state. I don't really want to pass that. I mean, I guess it's time to pause again so I can think about this particular problem. I'm not sure what I want to do here. I had time to think about it, and I know what's been confusing me, and it's this thing here. We're going to redo this. You know, actually match. out with, if it's, you know, some x, then we can just do this. There's no need to add anything to the dictionary anyway, or I mean the hash map. And if it's none, then we just do the regular thing. And why is this important? It's important to me because we don't want to have duplicate. I mean, we don't want to have offsets for the same node in both the node itself and its output nodes. If it has an output node, then we shouldn't be putting anything in the dictionary as the current offset, because we might otherwise get it by accident. And this would break shit. Yeah, that's perfect. And this is good design, because now in the future passes we don't have to think about whether we want to get the offset from the current node or from the output. That confused me. Now let's see. Yeah, here we have the tensor extract x, and that's perfectly fine. This f function doesn't have to touch the output node, and this particular function could just do that instead. Let's see, map and then map what? Out, and then what? What do we do with this out? Well, we call, yeah, we just call the loop recursively on it, loop out, and only if it's sum. If it's not, then we just get the what we need from the current index. Okay, so I'll get current for all t get current graph, and over here we have to check whether it has like fuck it, I'll just rename this to f. Who wants to keep on writing loop? Loop. And then what do we want here? We only want this if it's sum. Okay, we'll keep it as loop, whatever. And then we'll do this sum out and row map, row reduce. This is good. And otherwise, just get it from the current graph, no problem. And we don't need to factor this out, we can put it back where it was. Yeah, this is a pretty good solution. I certainly like it. Just out of curiosity, if we did that, then we get a type error here. Yeah. Yeah, this is the perfect way of extracting the output tensor. Because now we don't have the offsets for the current graph, when these nodes have the output nodes, we'll get an error. And that error, that's very illustrative of what's going on. Not bad. Zip apply weight input scalar. Perfect. Okay, and we have that now. We need to pass in the out nodes. Okay, for this step that already exists, we'll just pass the output node as none, no problem. None. Do we have any type errors? We don't. What we'll do is copy this discrete sample and we'll also pass it the output node. As sum out. And that can be an arbitrary thing. Now, let's try modifying this test. Instead of this, we'll pass in. Okay, let's make it. Yeah, we need the apply. We need the apply node. You know, apply. Dim first, the dim second, T. A graph tensor. Fuck this. A B. Who's going to keep writing all this out? T, and then what? We also need B graph B, just B, and then this will return graph tensor B. No, actually, yeah, like that. We apply the first value, then we do apply here, apply AB. And what is the problem? We need exists. I mean, do we really need an... yeah, we do need an existential inside, because it wouldn't be possible to... because all the existentials need to be used in the body. Okay, so we have the apply, we have the input, we have... yeah, we need the input scalar. And this doesn't have a dim, it has a key. And then what? This returns a graph of T. Input scalar is this key. Okay, so that's fine. It's perfect. We'll have an input tensor and we'll just apply. Okay, let's do that. Here's what we'll do. We have an input. It will be called output, It will be what ensemble and 16. We omit the second dimension here because we're doing a reduction, and it needs to be applied. Apply, and then you apply with what? With input scalar, and this will have what exactly? Yeah, the ensemble. Yeah, let me check out the matmul ensemble. Input scalar exists ensemble. Okay. I can just do like input scalar ensemble. And yeah, that's what we'll do. Input scalar ensemble. And we're applying this. And what is the problem? What's the problem? Fails to satisfy number. What's the problem? I mean, discrete sample got expected, apply, constraint satisfaction. Discrete sample. I mean, let me just take a look. I mean, shouldn't this has a complete type annotation, so it shouldn't be. Wait, and this. I mean, tensor I32. Did I maybe forget to put in? No, I didn't. Oh wait, but it should come as the first, not the second. Yeah, the output should come as the first element. Oh yeah, now it's perfect. And this implies the ensemble dimension. Oh, not bad. Now we have all of this. Let's see. Yeah, we are iterating the inputs through all the outputs of the ensemble, and the tensor output graph tensor extract. No, we don't need that anymore. We don't need that anymore. What we need. Yeah, does the input have the ensemble? We could also apply the. No, I mean, no. The input needs to be the same for all the models in the ensemble. So we do this graph run host model. That's perfectly fine. And then we have to not the graph extract, but the input extract. Output, and then we just print the output, and that should give us the entire. That should give us all the outputs in the ensemble in one tensor. Yeah, we have the output here. So yes. Okay, let's try running this, and we get an error. pattern means exists key as X line 237. 237, and that's which function exactly? Input extract. Oh yeah, we don't have the apply. We forgot the apply in this function. Let me put this above. So what exactly, if we have the apply, okay, we can do it much like the zip. Okay, let's duplicate this. We'll apply exists hey, and yeah, if it's successful then it's fine. Yeah, this should be it. Let's try running it again. We get another error. Another pattern is this time is in a different function. Wait, it's on line 41 again. Input scalar exists ensemble. Okay, let's see. Input scalar. What do we do with that? I mean, yeah, this is supposed to be extracting the tensor. So input scalar should just return none. Then if we build it again, we get another error. And type error in nominal constructor. Oh, this is nominal recreate. Oh, we're trying to recreate an I32 as F32. Oh, that's definitely not good. That's something we need to think about. Wait, why are we trying to recreate an integer as a float? Let's see, this input layer is an I32. The output is I32. Yes, this output is I32, and this is also I32. Okay, where are we using nominal recreate? Right here. Why are we trying to do that? Let's see. This should be. You should be trying to get the output here. Oh wait. Oh, I understand. I think yeah, we put in the float. Instead we need to put in an int. That's where the mistake was. Now if we build it, it builds. And if we run it, will it run correctly? Will it run correctly? Here's the output answer, and we forget to print it. Okay. Output, build, compile. Oh, this definitely does look correct to me. Yeah, I think we have a winner. How do we print the entire tensor? Okay, let's take a look at the primitives just for a second. And here we are printing tensor print ln. Okay. And this should be like limit max, whatever. Let's build this. Let's run this. Now it printed out everything, and this does look correct. And yeah, now with this library we have fully functioning ensemble models. Of course, when we run a model, we want a discrete sample, but we also want all the path probabilities. So, how do we do that? What we're going to have to do is add a pair node, and instead of a discrete sample, we're going to have to, the way that the discrete sample is implemented right now, it does a softmax internally for efficiency, but that kind of efficiency is not good for us right now. We want to do calculation step, and we do want to preserve the intermediate softmax in global memory. So what I want to do, okay, I'll just add a node here, and we'll actually be implementing it for tomorrow. Let's see, pair and dim AB. I mean, they'll have the same dimension. And wait, this won't be tensor AB, but and the tensors might not even have the same dimension. Dim A, dim B, B, dim A. In fact, what the hell am I doing? A, B. We just have the graph A. We have the graph B. And we can just return a pair of graph A and B. That's pretty good. We'll have to add, we'll have to implement all the passes for this pair node. But after we do that, we'll be able to output both the path probabilities and the sampling results. And I really feel like leaving that for tomorrow. Who wants to program anymore? I've been at it the whole day. Okay, but before we end it for today, let's just actually implement the model itself. And let me also do a pair graph A and B, and this will be pair AB. And now we'll have pretty much the same, I think. I mean, a very similar test. Which keeps around the path sure about this. Okay, here's the actual model. And we don't need to pass it through a softmax. Let's see, softmax. Inner x. And let's see, this will be pair x and the discrete sample, but instead of the discrete sample, it needs to be something else. Let me think. What does it need to be? Okay, let me think. Pair. Let me take a look at the primitives. We have the exclusive sum, recursive x, where is the script? Discrete sampling, for fuck's sake. Discrete sample, look at primitives, discrete sampling. Okay, and we have this here. And we're doing a softmax, and then we're doing a scan sum, and then we're doing a sampling step. And what we want to do, what we need is essentially this function without the local softmax. Okay, let's do this. Softmax and discrete sampling. Now this should break everything, and that's exactly what we want. And weird that it's not breaking anything here. I mean, it should. Okay, we'll still keep this library around for a tiny bit longer. We're going to get rid of it in the future. Okay, now we have this, and we'll implement the primitive for the discrete sampling and name it properly. And that's actually very easy. Local softmax. Local discrete sampling. And this is x. And this thing, we'll just do this, and then let's see, energy config ij tensor, and we'll just do a local softmax like right here. And this is how we factor things out. Yeah, we do a local softmax, then we just pass in the output. Perfect. And yeah, now we can implement proper discrete sampling. But before we do that, we actually need to do some renaming. Softmax and wait, do we have a type error? Oh yes, I do. And oh yeah, we have this type error here, but we'll fix that. Okay, first let's put in quark here. We'll get rid of this one here. And what do we do here? We'll put a bookmark, and then I guess I'll just copy paste all this. And we'll just do this. Now we have set up the model. Now we have a softmax here, and we can just use we can just use a discrete sample. And the previous one, yeah, uses the softmax and discrete sample, and this one is just this discrete sample. Wait, yeah, it needs to take in an output like this. And why is this giving us an error? Tensor II32. All right. This is expecting a graph int. We're giving it something completely different. Okay, let's copy this. Perfect. And now what we've done is set up the entire graph. Yeah, we need the path probabilities for the softmax. And we need the softmax to have an output. And okay, this will be the output and this will take in something like apply input output probs, and it will have size of let me think, ensemble, yeah, 16 in this particular case. And we'll be applying the input scalar ensemble with it. Input scalar ensemble. Per x. Okay, the only problem is that we don't have this softmax function, so we're going to implement it right now. Let's see, where is the softmax? Here is the softmax. We'll just do this, and then also take in an output parameter, and then sum out. And yeah, this is, yeah, it worked right away. Oh yes. And after it's done running, we just have to print out not just a single tensor, but output probs. And this one is I32, F32. In fact, no, it has like it's tridimensional int, and yeah, whatever. This one will be output indices. And you know, this 16 times 16 is 2 to the 4, 2 to the 4, 2 to the 4, It's going to print out a lot of stuff. I mean, it's going to print out like 4,000 elements in the terminal. I mean, 2 to the power of 12 elements. And this one is like 2 to the power of 8, which is 256. But okay, so let's limit this to something like 1 to the power of 8. And yeah, we need one more. Okay, now that's to the power of 8. And we can try building this. Let's see whether it works. And this should be test 5. Now let's run this, and we get an error. Oh yeah, we have a pattern miss because we haven't implemented the pair pattern anywhere. And I don't feel like doing that right now. Well, we'll just put in a bookmark here, and then we'll get rid of this one here, and we'll resume tomorrow. Let's just make a quit. Well, excellent. We did pretty well for the day. I think we've fixed an error in the language. Then we had another error which wasn't really an error. And we understand how GADTs work much better. The GADTs are getting filled in correctly. Okay, this thing here. Okay, this thing here is pretty much useless. Whatever, we'll leave the test as it is. I mean, we can also get rid of it. We'll leave it as it is. And yeah, great. We don't need the Visual Studio IDE. And yeah. The mic still works, and we'll stop recording here. I'll see you tomorrow. Tomorrow is also another day where I'm not going to the beach. Today I didn't go because my back muscles are really killing me when I try to move my hands upwards like this. So I don't have any business swimming today. In 2 days I'll go to the beach again, and I'll only manage like an hour or two a day, maybe even 3. It's a pretty slow summer, but we're going to get this machine learning library done. You can count on it. And after we get this machine learning library done, we're going to train the reinforcement learning agents. We're going to implement that cross-entropy method that I talked about a couple of videos ago, and it's going to be great. If the RL agents work, I'm actually going to put in a bit of extra effort. I'm going to put in a bit of extra effort, and we're going to try out the agents on at least the play money sites. It should be pretty interesting how to do all the UI automation. I know that one, hidden poker forum had a program for this kind of thing. It was written in a bunch of Perl scripts. It's probably putting spyware on my computer. Yeah, it would be an interesting adventure after the RL agent is done to actually try it out with real money, because that's the only thing that really matters. And did I say real money? I mean play money. Play money is what we'll try it out. And only if we can actually win on the play money tables, we will try it out with real money. And I don't think these algorithms will be good enough for real money, but one can always hope. I mean, people are making money using machine learning in financial markets, so maybe we could manage to do something in poker. The main problem is that the algorithms are absolute shit at the present date, which is July 11th, 2024. We'll continue tomorrow. I need to go have lunch. Okay, the mic works. Let's resume where we left off yesterday. Yesterday what we did was create an example for the pair node. And what we're going to do today is actually implement all the pair node cases for the various functions. Let's do that right now. So we have, okay, first we have the getDim. Pair is, yeah, it's similar to zip, I think. I mean, is it? No, we don't need to actually do an assert. Oh wait. It takes a graph tensor dim top. What about the input scalar? Okay, I just realized if the getDim actually takes in a tensor input in the top level node, so the input scalar and the pair would automatically be eliminated from that. Like suppose we try doing a pair here, pair AB equals fail with. Let's just put in a placeholder here, and in fact it will get an unification failure. As you can see, it's expecting graph on tensor d top, and we are giving it here a graph of two pairs. I mean, not a graph of two pairs, but a graph of a single pair. So yeah, we can just keep it here. Now here, yeah, here we definitely will need it. Let's see. Yeah, we can just copy zip pair. Perfect. Okay, now pass offset output. This is also a pass through pair. Pass calculate dynamic memory. Yeah, it's pretty much the same thing. Yeah. Parameter initialize. Once again, it's the same thing. Parameter print. It's the same thing. I copy pasted it. Input extract. Let's see. I guess we'll just copy this as well. Okay, let's do. I mean, we'll just leave it like this. Fuck it. I thought of maybe factoring this out. Let's factor it out. And pair AB equals and now I'll just do pair AB. Pair AB pair AB, pair AB, pair AB, one, graph A, graph B, option tensor dim input. Okay, let's for A, B, A, graph A, B, graph B. Okay, perfect. I mean, I don't feel like factoring this out, but this case was kind of verbose, so I wanted to do it. Oh, not bad. Oh, graph tensor extract. Oh yeah, this is oh, graph T. It gets T. Okay, I'm not even sure what this function is supposed to be doing for the pair node. I'm going to have to pause to think about it a little. I mean, the zip obviously zips, the apply applies, the input scalar does what it does, but this thing... Oh, I think I understand. Okay, how about this? Pair, loop A. Yeah. This is exactly it. TDTE, and this is TD, and this is TE. Okay, yeah. I like that. Perfect. Graph run. We'll also do pair. Yeah, not bad. Graph run device, graph run. Yeah, I think we have everything we need in order to actually see the pairs. Let's just make the output a bit bigger so we can see like two vectors of the ensemble, or two matrices of the ensemble, I mean. Okay, let's try building it. Spiral build file, and we get an error. Let's see. Type error in the nominal constructor. Tensor body I32, tensor body F32. This reminds me. Wait. This is 3-dimensional. This is 2-dimensional. Okay, well, what's going on? Yeah, this is. What's the type of this? Yeah, this is probably the. Yeah, this is the 3-dimensional tensor, and this one is. Yeah, I32. I'm just a bit confused. Oh yeah. As you can see, this is probably an input extract. Yeah, this is an input extract. It's very easy to make this mistake. We've done it like twice already. So let's see. What's the type of output indices? I32. Okay. Perfect. This should be it. Let's build it. Now let's run it. Okay, what's going on here? I'm a bit confused. The output tensor is on zeros. Did we even run the graph run host? Then we get I'm not sure what to think about this. Here are the weight matrices. Yeah, there are 3 weight matrices. The output tensor. I don't understand. Let's try running the previous test. I mean, this one clearly works. And this one doesn't. Okay, so we definitely have some kind of error in this code. I guess we'll have to go step by step and debug it. Okay, so based on test 4, we can be sure that matamul ensemble works. Okay, we're going to have to do some sanity checking. Let's start with this. And let's try to get the softmax working. Input scalar, ensemble, output probes. Okay. We'll focus on one thing at a time. Maybe there's something wrong with the pair. So if this works, we'll be able to isolate the error. Oh, okay, great. This is supposed to have like 16 elements. I think this is fine. Okay, so the softmax does work. Okay, suppose we did something like this, pair XX. and then I'll just copy paste it like this. Then what exactly would happen? Yeah, now we're getting zeros pretty much everywhere. Okay, let me pause here just for a moment. I'm back. Now, what I want to do, let's also comment this out. We'll comment out everything except the input. And yeah, the type is still correct. And this outputs a pair. Now let's see. Let's build the file, and we're getting an error. Can I find the input answer with the given key? All right. Wait. Okay, I see. Let's try printing the input then. Wait, I'm already printing the input out. Oh, really? Here the weight matrix says. Here's the input. Oh, it is outputting the input. Okay. Here's the input. Here's the output answer. Okay, let's do this. Spiral. Okay, so this works. Let's check out the matrix multiply ensemble again. In fact, let's do this. We'll build it, we'll run it. Oh, and it is getting the input answer. Okay, so now I'm pretty sure that the input extract is working properly. And the weight matrix says yeah, there. Okay, let me think. If you get the output probability is and what if we instead extracted the output tensor? Let's see. Instead of doing this, we'll do graph tensor extract, and then what? How is this being used again? We need to pass in the model and the indices. Okay. Okay, model ensemble equals 0. Okay, let's try it like this, and this one doesn't need a type annotation. Okay, we can just print out the first What I'm testing here is whether the graph is being run at all. It seems like it isn't. The reason why we're getting zeros everywhere is because I think the graph isn't actually being run. Oh yeah. Oh yes. I understand. Okay, let's go into the graph run function, and we'll see the problem right away. When we get a pair, we're just extracting the tensor, but we aren't actually running the nodes below it. And that might actually be a problem with the zip as well. Zip. Yeah, that's we have pretty much the same problem with the zip. Oh damn. We have the problem with the zip, and we have the same problem with the apply. Pair zip apply. Crap. Okay. Okay, and then yeah, we do need to extract the tensor for the current node, but we also need to execute the ones below it. Okay. Okay, let's do FA, FB. All right. I think I understand. Okay, let's do this. FA, FB, FA, FB, FA. Actually, wait, is this really right? Oh yeah, I mean, we're taking a tensor, and the tensor should come last, and we're applying the first element to it. This is basically right. Okay, I see. I see. We did have a bunch of problems, it turns out. So, I think I was a bit too hung up on how it was done before. Okay, tensor extract, and it's fine to have these cases here. Oh yes, okay. Okay, I think it should work now. Let's see. Discrete sample. Graph. Here's the input tensor. Here is the output tensor. Okay, let's see. Let's try running this. Run Control F5. Oh, perfect. Here's the output tensor, here's the input tensor. Oh yeah, this is perfect. I love this. A model like this, which returns a pair of the softmax output and the discrete sample, and you'll note how these two tensors don't have the same number of dimensions. This would have been completely impossible in the previous machine learning library. In other words, in this one. And this is like the primary reason why I decided to get rid of this and go with the GADT approach. We can get rid of this now. And we'll rename this to just layers. Wire mechanic drama. I accidentally put in a character in a random place, so that's why it happened. Okay, now we can just we can open the layer spy again. Let's just compile it. Build file, layer spy. Let's run it. Great. I'm very pleased by this. Okay, and now I'm thinking what we should do next. We could also distribute the input across blocks rather than just the ensemble. I think that's the next frontier. Okay, let me pause for a bit here so I can think about it. let's just get started. What we're going to do is do something that is do what we talked about earlier, which is adding apply block to the language. Let's see, here we have the apply. What we'll do is now this is just do an apply block. And this will just be like this, int yeah, this is very simple. And oh wait, okay. Suppose we try doing something like, graph tensor extract, but we do it on host. Then where exactly are we supposed to get the ID in that case? It's easy to get the ID on the device side, but what about the host? Okay, that's a bit more complicated than I thought. So okay, we won't be adding this node to the language then. We're going to have to figure out how to apply the current block index inside the kernel itself. Okay, let's just duplicate this thing. Okay, let's do in block equals blocks Corcuda base. Now where are the blocks per grid? Yeah, that's what they're looking for. Blocks per grid. Then this will have a block. And we also need to apply it now. Apply. And this will be input scalar block. Yes. So far so good. And we're going to find a way to insert the block inside the graph run host. Let's do wait. So now this is no longer right input. And let's go into graph run host. Okay, I remember trying to just extend the indices directly, and it didn't work. But we're going to make it work this time around. Okay. So how exactly do we want to do this? Okay, let's do indices with the block equals block index. And if we do that, we get a type error. Expect a record got sizes. Suppose we try doing that in the bottom-up segment real. But now it's complaining about a meta variable. Yeah, that's the main big issue with this. And some graph run device indices. I mean, in this case, we can just lie about the type. Okay, let's do indices. Indices. Oh, this is sizes. I could only sure. Okay, we could always just do this as well. Real, and then just infer the type of this whole thing. Indices. Oh yeah, we can just do this. This, no, not this. And what this expression does is infers the type of the indices, but I think graph run device, yeah, it has two for our variables. So whatever, let's do t-top. Let's pass this in, and yeah, this should be good. And this doesn't have a type, but it doesn't matter since it doesn't need to actually apply the meta variable anywhere. You know, when you see this indicates that it's a meta variable, but you only get value restriction error if you need to apply that meta variable to some function, and it cannot infer the exact type. Okay, let's see. Graph run device, t-top, indices. I mean, yeah, this fine. Or actually, no, this isn't fine. We're doing this in the wrong place. We should be doing this in graph run device instead, because this is the place where it makes the most sense to actually put this in. Okay, let's see. And now this graph run is causing trouble. You know what? What the hell? You know, it's not like this. It's not like this has any restriction on the for all variable, so we can just do this whatever. Indices. Great. Now it will just pass a simple as a type, and this. Yeah, this kind of type lying would have disadvantages if the user tries to put the indices into an array or something like that. Yeah, okay, we'll do it properly. Whatever. Graph run t-top indices. We just do the same thing we did before. Real t-top, and this is indices. What this does is simply takes this expression at the type level and returns its type. I think C++ has a similar capability where you can take the declared type of something and return its type. Actually, let's look that up really quickly. CUDA user guide. And the reason why we're looking at the CUDA user guide is because I cannot remember. Oh, for fuck's sake. CUDA programming guide. And if you look at the cooperative groups and then group collectives, and notice data manipulation. Oh yeah, the call type. That's what I meant. C++, the call type. You give it an expression, and the call type gives you back a type which responds to the type of the expression. I can explain this. The call type simple P4. Yeah, this is it. And in the old version of Spiral from 2018, pretty much all type inference was done like this. And it's kind of funny, because Spiral was a statically typed language, and you looked into some of its code, and you'll see that it has much less type annotations than a language like Julia. Even so, this kind of programming got tedious really quickly, because I had the program for an entire session, and then I just go ping pong from type error to type error for like hours afterwards. It's like programming in a dynamically typed language, pretty much. I very much loved it at first. It was a pretty novel experience, but then I realized just how awful that kind of programming really is. So I put in the effort, and I have built what you see here, which is this top-down segment. And we have the type annotations, we have the for alls, we have the type inference, and that makes programming a lot easier. And I think this is like the first time we've actually used this technique in a useful manner. Let me just what's the type of this? Yeah, it's t-top. Okay. I'll give it a type, even though we don't really need it. T-top. Oh yeah, not top, but t-top. Maybe it will be useful in the future, though I doubt it. Okay, this is graph run device. And doing it like this is a lot better than having to add node to the language. It's certainly much less work. If we added a node, we'd have to modify every single pass, and that can get pretty tedious. Okay, let me think. So we do have the block. Okay. Go through input extract model, output probabilities. And we definitely don't want to just pass the block size in the input directly, because oh wait, I just realized something. Oh yeah, here we have the graph run host, and then we iterate over the indices, and it's very good that we don't have the block in here, because otherwise it would iterate over the block in a linear fashion instead of distributing them across the actual GPU blocks. So yeah, that's fine. Yeah, the only thing I'd maybe want to test is that, let me just put a little test, a little real match sizes with block error type. Yeah, we don't need a type annotation here, I think. Or actually we do. Okay, let's do real core error type. The block will be applied, inserted in graph run device. Run device. It shouldn't be passed into graph run host. Automatically. Okay, that's just a little test. And in fact, we'll also put it here. Match indices. Yes, okay, I like this. This is how you can test whether a record has an element. If it has, then we'll get this type error, and if it doesn't, well, unfortunately we'll get a pattern miss. So we should also just do this. Okay, not bad. And this isn't necessary, but it kind of serves as documentation. You know, when somebody reads this, he'll know that the block index is automatically inserted into the dictionary. Maybe I'll forget where the block is being inserted and have to read the source, and then I'll figure it out again. Okay, now this is fine. We have two test 2s, test 5s. Now we'll rename this to test 6. Yeah, we are applying the input scalar block. Perfect. And right now this block's pretty good. this blocks per grid value is just 1. So, but if we go into for example, into core CUDA, and we ramp it up to, I have a RTX 4060 in my rig, and it has 24 streaming multiprocessors. Okay, SM's RTX 190. Fuck you. Tell me what the number of string multiprocessor is. Oh, 128, yes. And right now we're still just debugging. You can see that we're using 32 threads per block and only 1 block per grid. So, and that's fine for now. Let's just compile this file and we'll... wait, what's going on? Cannot apply a for all with the term. Oh, really? Oh yeah, this model M, we're doing something to apply that. Let's see, what's that? What's this model? Oh, right. Yeah. And because model M. Yeah, this is the model itself. And okay, this should be fine. Now let's try building it again. We've only built test 5. Now what we want to do is build test 6, which is this new example, and it has built. Let's just make sure that it hasn't crashed the compiler, and as expected it didn't. Now let's try running it. Yeah, I'm really wondering about the input tensor. Here's the input tensor. As you can see, we have at the very start these 3 opening braces. That indicates that the entire tensor is tridimensional. So that's pretty much what we could expect. And yeah, this is excellent. Wait, why are there problems? Learn. Oh yeah, I think we broke Leduc when we erased the old library. Where are we even importing it? Core CUDA main test2. Open ML layers. Oh, I see. Whatever, let's just comment this out for now. We'll get back to actually running the model on the game a bit later. And yeah, as I was saying, now we can very easily distribute the computation across all the blocks of a grid, and that means we can easily distribute the computation across the entire GPU rather than just a single block, a single SM. I mean, yeah, the result to be happy here. We can very easily run in ensembles. Using this model, we can very easily distribute it across the block. We have the softmax, we have the sampler, we have the layer normalization. Yeah, let's do a commit. We can distribute. I'll just put a little comment. Gets passed inside of what? Graph run device. Okay, let me just think about this aspect for a bit more. I mean, we're passing it. Sure, we're passing it here, but maybe we should also be passing it. No, not inside tensor extract graph. Maybe inside the graph run. Should we be passing it? You know, right here. Let me pause just a bit so I can think about this. I decided we're going to in fact insert it here. It's better to do that closer to where it should be. So, okay, oh my god, we just keep shifting this. Graph tensor extract the indices. indices, and now let's do this. For T graph, and this will be real real I think it yeah, it should be done. I think it should be done. Oh crap, now we have to do the model. But okay, let's do model equals. I can't be bothered to figure out how to apply this manually. I mean, yes, we need a colon. And what I want to do is, in fact, wait, fuck, now I'm playing the model in the wrong place. Okay, this is driving me crazy. Let me just pause for a bit so I can figure out how to organize it. I look like a complete moron right now. Okay, here's what we're going to do. It isn't worth the code complication of having to do manual type inference indices. Let's just do this. Fuck it. And we also, what we'll do is get rid of this assert. We'll also get rid of this assert, and we'll move the assert. Remove the assert. We'll move the assert here. It. Beforehand. No. Okay, let's see whether it still compiles. And it in fact does. Oh yeah, no problem. Okay, we can distribute the computation across the blocks, across all of the block. We can distribute the computation across all of the blocks of a GPU now in the machine learning library. In the yes, this is perfect. Who knows? It's actually possible to design the machine learning library in an alternative fashion. For example, who knows? Maybe we could design the library so that instead of doing block synchronization, it did grid synchronization, and this would make it a lot easier to do. I mean, to implement something like backpropagation. In particular, the backpropagation algorithm requires the matrix transposes during the backwards pass, and you cannot do that if you are splitting the input matrices across the blocks. You have to split them across the entire grid, if it makes sense what I'm saying. I mean, if it doesn't, you can kind of look at the intro to backprop in Spiral, and you'll see that it's actually very difficult to do the backwards pass for the matrix multiply. If we wanted to do it with the current design, we might need to use atomics to sum up the return results. I mean, to sum up the gradients for the weight matrices. And not to mention, doing it like this really, I mean, it doesn't completely block batch normalization, but mostly it does. Also, for convolutional neural networks, it might be better to actually split, split the inputs not across the blocks, but across the grids as well, because the inputs are so large to begin with. So multiple blocks it might be better for multiple blocks to be responsible for a single input. Visual data takes a lot of power, computational power. But we're doing reinforcement learning here, so I think this kind of library design is fine. Okay, let me think. What exactly do we do? What exactly do we want to do next? We have blocking now. And do I want to do anything else with the library? I mean, I have the path probabilities as the first part of the pair, and the selected index as the second part. We also have a very easy way of actually extracting the outputs using the input extract function. Do we have extracts the input tensor for the given key? Extracts the input tensor from the input node from input nodes given the key. Okay, not bad. Maybe it's time to start thinking about actually integrating this library with the Leduc game. I also said that maybe do some, we could do a more succinct graph that compiles to this more complex one, but I honestly don't really give a shit. The reason why I did that in the first library because it was possible and I wanted to make it nicer. But in the end, what really matters is that we have the functionality that we need. We can also, make flexible models even with the current approach, like we can just substitute these with variable sizes, and this could be like S1, S2, 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 S3, and this would be, I don't know, S3, S3. So, I mean, I could be wrong, so sorry about that. Like this could be S3. Yeah, if this is S2 and this is S3, this should also be S2 and this... I'm not sure. Okay, it doesn't really matter too much, but just keep in mind that we can very easily bind the shift-signal sizes, but by making this S2, S2, S3, S3, S4, and if we had another layer, we could just pass that as the first element, like S4 here. Yeah, like that. And that's a bit less ergonomic than having the input sizes being, having the weight dimensions being inferred during the first run, but it's fine for now. It's more important that we actually get some useful functionality out of this library. So we'll leave the redesign for later. And I'm not really even sure. Here we are using pretty much, if you look at this model, we're using pretty much every single node there is here. I'm not sure we can actually do a simplified compilation. We could have something like the previous design and automatically insert these input scalar block and input scale and ensemble applications. It could work like that. But whatever. Okay. Let's move on. This is perfect. And just as I said, this is perfect. We don't need to think about it anymore. Learn base and where we left off a few videos ago is we are working on actually serializing the inputs into the Leduc game, and we had this graph. We have this discrete sample. Okay, let me pause here so I can think about what we should do next. It's really great that we completed the library with the GADTs, and it actually might be a good idea to end the video here. I'm doing a live stream, and as it is, the video is over like 7 hours long by now. I'm not sure at all who will watch this, but I want to try doing live streaming for a few videos just to get used to it. It's a lot easier for me to speak than to write things out, even though it wasn't like that at the beginning. I guess I've gotten used to speaking to the camera. And initially, back in early 2023, I picked up doing YouTubing so I can improve my talking skills. And maybe I've gotten a bit better at that. What do you think? If you agree, like and subscribe, and I'll see you in the next video.